recording isn't that important, but it's fine. So here's my idea of the plan for today, guys. Okay, so we'll finish chapter 11, or whatever the chapter. Let me find the exact number. Oh, I don't have Google Chrome open. Hold on one second, guys. I gotta log into now. Log into to get the practice problems. Okay, so we'll finish, chapter 11. Okay, first point. I'll just type. Finish chapter 11. Okay, that's angular momentum. Okay, then is finish, well, do chapter 12. Okay, chapter 12 is static equilibrium. Okay, just spell that right. And then after that, I'll try to find some practice exams. Final exams. And so that kind of summarizes everything, right? Everything in it, right? But then if there's specific other topics from earlier in the course, so earlier course material, we'll finish off with that. Okay. So that's generally my plan for today. Does that sound good with everybody?
Yeah.
Okay. And yeah, I'll try to have discussions open. So I can see that. But yeah, okay. So let's start with where we left off yesterday with angular momentum. So we did number 19, I'm pretty sure. Number 19, let's find it. Just make sure we did number 19. Big Ben, yeah, Big Ben with the clock tower. Okay, what's next after 19? 22. This one. 22. Okay, well, this looks like another big one, so let's give it a try. Okay. Just gonna get this. Oh, do we have the answer for this one? Yeah, the answer's in the text. Okay. So, you are working in an observatory taking data on electromagnetic radiation from neutron stars. You happen to be analyzing the results from the neutron star in some example, verifying that the period of the 10-kilometer radius neutron star is indeed 2.6 seconds. You go through weeks of data showing the same period. Suddenly, you analyze the most recent data, and you notice that the period has decreased to 2.3 seconds and remained at that level since the last time. You ask your supervisor about this, who becomes excited and says that they have a neutron star that must have gone under a glitch, which is a sudden shrinking of the radius of the star, resulting in a higher angular speed. As she runs to her computer to start writing a paper on the glitch, she calls back to you to calculate the new radius of the planet, assuming it has remained spherical. She is also talking about vortices and a superfluid core, but you don't understand those words. Okay. Wow, okay. So, okay. So, we have the original radius. Its period was 2.6 seconds. Okay. We have the new period, 2.3 seconds, right? And we want to figure out what that radius was. Okay. So, well, let's turn this into angular speed. So the initial angular speed, right, is, sorry, I have something in my throat, is, so you do 2 pi radians, right? 2 pi radians all the way around the circle once, like it spins all the way around, 2 pi in 2.6 seconds. Okay, so I'll just divide that out and then I'll have a number for that. 2 pi over 2.6. So that's 2.42. So 2.42 radians per second. And what's the final angular speed? Oops. The final angular speed is, it does 2 pi in 2.3 seconds. Right, so it's going to be bigger. So it's going to be 2 pi divided by 2.3, which is 2.73 radians per second. So we know that. We also know that the initial radius was 10 kilometers, right? 10 kilometers. And the final radius, the radius final is our target. We also know that the angular acceleration is 0, because it's steady at that rate. Like it stays steady here, it stays steady here. So how would we calculate the radius just if we knew this? We knew these two facts. We know the speed. We know angular acceleration is 0. Well, we need to somehow relate. Let's see. Let me think of some equations I could use. You don't know anything about, although this is called angular momentum, isn't it? Yeah, this is called angular momentum. We don't know m, but let's just say we assume, let's just call m, right? M is the mass. So let's say mass. Mass equals m. So, so since it's saying that we have to use angular momentum, because it's like an angular momentum question, it says that at the start, up here, it's like a title. It says angular momentum question. Then, what do we need to find? We need to find radius when that's true. Looks like the only time radius appears in a question is when you're...
I have a theory. It might be wrong.
Yeah.
Maybe.
Let me know. What is it? Yeah.
Sure, we have that our angular speed changes, but I don't think our linear speed changes. Because linear speed is dependent on radius, right?
Yeah, I think that makes sense because they said that
Because
the
both
glitch is
times
decrease in
the
size.
glitch just means that it's shrunk in radius. And that like the same linear speed would result in a smaller radius because that's how you go from linear speed to angular speed.
Okay.
Maybe.
But we don't know anything about linear speed either. Here. You see what I mean? We don't know there's no other information about that in the question.
We do know the radius and we do know the angular speed. There's a relation between them as well.
Okay, so convert that to... Okay, I can convert that to linear speed. And then linear speed will be...
Yeah. The same.
The same?
We'll
Yeah.
see.
Oh, I see. Okay,
Maybe.
yeah. Linear speed will be the same.
Maybe.
You're right.
Okay.
No, that does make sense, actually.
Maybe.
Well, then, so then I could... This is pretty short then, actually, because then I can just say R I omega I equals RF omega F.
Yeah.
Yeah, and then I just say RF equals RI omega I over omega F. Oh yeah, can everybody see the second stream? Someone said in the chat here can see. No one see the second stream, but hopefully people watching the second one can see. RI is I'll do 10,000 meters. Omega I was 2.42, and this is 2.73 for omega F. Let's see if that gets the right answer. So 10,000 times 2.42 over 2.73. So I got 8.7 kilometers. And is that the answer? Close, but not exactly. 9.4 is the answer. So we're not like far off, but did I type a number in?
Post the solution in the discussion. Apparently, we're supposed to use like the conservation of angular momentum, I think.
Okay, then let's try that. Yeah, okay. Let's try that. So, well, I don't really know why that didn't work, but yeah, okay. So, Li. Someone's got me on speaker, and I can hear myself talking through. Li is equal to Lf, right? Which means the inertia times omega I equals, well, I guess inertia I times omega I is equal to the inertia F times omega F, right? It's conserved because there's no torque acting on it. It's just closing its radius in, right? There's no like torque happening. So momentum is conserved. Angular momentum is conserved. So, well, what is the inertia for a sphere that's spinning? Is it just the point? You just call it the point? Or no, here. Well, this thing is, again, bad quality, but I think it's 2/5 mr cubed. I think it's 2/5 mr cubed for the inertia for a sphere, a full sphere. Maybe someone who has a better quality picture. Is that correct?
I think it's 2/5 mr squared.
Okay.
It's squared.
I can't really see. That's the one thing I can't really see the exponent. So
It's a cylinder.
it's a cylinder.
So
Yeah,
so
you
it
use
should
the
be
cylinder.
1/2 mr squared.
Yeah, that's how I got 9.4.
Why is it a cylinder?
Either way will cancel out anyways because you're gonna have it on both sides.
It says that it's a uniform cylindrical turntable.
I think you're. Wait.
Oh, sorry. I'm
question.
looking at the. I'm sorry. I'm looking at the wrong one.
Don't worry. Yeah, there you go. So I sphere is 2/5 mr cubed. Okay. Mr squared. We said mr squared, right?
Yeah, squared.
So this is going to be 2/5 the mass, which stays the same, the initial radius squared times the initial omega. Then again, 2/5 times mr final squared times the final omega. Okay, so that's what we're missing. We're close because we didn't have a square on both of our r's, right? So everything else is the same. So that's gone. That's gone. So it's just ri squared omega I equals rf squared omega f. So rf equals ri squared omega I over omega f in a square root. And that should be a f. Okay, so then that's ri squared was 10,000 meters. Omega I was 2.42. Okay, and omega f was 2.7 something, 2.73.
Sorry, I just wanted to ask. By the way, are they going to be giving us these I values for the different shapes, or do we have to already have them?
No, I think they're gonna give it to us.
Okay, thank you.
I think. I mean, I'm not sure, but pretty sure.
Oof.
2.42 and then 10, 1, 2, 3, 10,000. Okay, I got 9.4 now. 9.4.
You got it.
Yeah, 9.4 kilometers. That's the final radius. So yeah, so momentum is conserved. So we're in conservation of momentum, I guess now. Angular momentum.
Oh, so wait, why was the first one wrong again? What were we using?
We use this, and why was it wrong? We converted to linear.
That's why. Because when you put ri omega
Yeah.
I, it should be I squared. That's
Yeah,
why.
which makes sense when you do it like this. But why didn't this work? I mean, the logic of it is we converted to linear speed. Linear speed would be the same. Well, no, I
Maybe
guess we
linear speed
don't.
isn't the same.
I guess we just don't know anything
Linear
about.
speed, wouldn't it be the radius between the neutron star and its center of rotation? Like, it's giving you the radius of the neutron star.
Yeah.
So, like, technically a linear speed like that isn't correct.
Oh, I think I got what you're saying. You're saying that.
But won't linear speed actually increase?
Yeah, I guess so.
Probably, but we don't know the radius of, like, its path of rotation, so...
Yeah, that's true. Okay,
Linear
yeah.
speed would have been for the rotation
That's
itself.
true.
for
Yeah.
the entire-
Okay, so
yeah,
that just
I
like
understand.
it wasn't right. Yeah. Okay, so conservation of momentum that got us there. It was very close, just because we were missing the square. That's all we were missing.
Wait, can someone else stream it? My internet's horrible.
Okay.
I can't
Yeah.
watch it.
Yeah, that's true. So yeah, if someone else could do that, so we have enough. There we go. Thank you, Evelyn. Yes, good. Okay. So, that was that question. There we go. That was number 22. Let's go to number 25. Number 25.
Real quick, can you just show the question again because some of us can see because the stream wasn't on.
Okay, there you
All right, cool.
go. So 25.
What was the question asking for?
The new.
Because I wasn't. Yeah.
The new radius. So we had a planet. It was spinning at a certain rate, right? And then all of a sudden it shrunk and it was spinning at a different rate. We know this initial radius. We know the initial speed, and we know the final speed. We just have to find the final radius. And we do that by saying that angular momentum is conserved, which it is because there's no torque acting on it. So, okay, a uniform cylindrical turntable. Here we are. Sorry, just part A. Okay, so a uniform cylindrical turntable of radius that and mass that rotates counterclockwise in a horizontal plane with an initial angular speed of that. The fixed turntable bearing is frictionless. A lump of clay of that mass and negligible size is dropped onto the turntable from a small distance above and immediately sticks to the turntable at 1.8 to the east of the axis. Find the angular speed of the clay and the turntable. Okay, so omega I equals 4 pi radians per second. Okay, uniform cylindrical turntable. The full radius is 1.9 meters. Okay, mass is 30 kilograms. Okay, that's it. Then mass of clay, mass of table, mass of clay is 2.25. And then from small distance above immediately 60 turntable. And then the radius of the clay is 1.8 meters. East of the axis. Find the angular speed. Okay, so we have this. Make sure you mute your mics, guys, if you have stuff going on in the background. This much east of... how far? What was it? 1.8 meters. Well, that's a big turntable. Oh, no, it's pretty much at the end. Okay. So, like, right there, a piece of clay falls. Okay. What's the new angular speed? So, find the angular speed of the clay and the turntable. So, well, I guess we just do, like, what was there any force? No, there was no force. Was there any torque that acted on the turntable? Well, the clay falling on it, no. Force of, no friction that would slow it down, no. It's just the angular momentum that's going to be affected, so it's going to be conserved as a whole. So, the angular speed is what's going to be affected, right? So if I have the angular momentum initial, and I have the final angular momentum, that means that I initial, yeah, hold on, yeah.
Force that the clay exerts on the turntable when it falls.
Yeah.
The torque, because it's perpendicular.
But we did a question, but it's not like producing something that's like, because if you think about it, if you have something spinning, like we did like a thing like this yesterday. If you have like a thing, right, and then a thing, and then the pole goes through it, and that's spinning, right? Okay, well, it's like, it has a thickness, and that's spinning. If you like push your finger down on it as it's spinning, your force downwards is not what's causing directly the torque. It's the friction, right, that's causing the torque, because it's going like perpendicular in that plane to the rotation, right? But your force down is not what's causing that. It might just tilt or something like that. It's the friction that's causing the torque. So what I'm thinking here is that force of it hitting down is not causing any torque. And it's also not causing any friction because they specifically say it immediately sticks to the turntable. So it just adds to the mass. And yeah. The turntable clay system constant in this process. But I could be wrong. I don't know. That's just what I'm thinking.
I don't know. One thing I figure is like usually if you drop something onto something else, it's gonna slow it down though. Like it's a new mass, so has to move at the same speed or was moving at an initial speed, so it should slow it down.
It will slow down. It will slow down, but not because it has a bigger mass now.
Yeah,
Right?
I think that's the only reason.
Because it has a bigger mass, right? Only thing that's kind of confusing me is how I'm gonna take into account both of these radiuses at the same time. Well,
can we use the other formula for angular momentum?
Okay, yeah. So the initial one is just this is
MBR sine theta 1.
the thing is with that is that we don't. What do we know about v? How can we find v?
I think R might just be for moment of inertia, because for the disk, and then plus you're gonna have to change the moment because of the mass displacement.
Pardon?
Hmm. So I'd have to use this. I'd have to use L equals I. What was it?
I'm guessing. I don't really know. I can't say, but there's probably a formula for the inertia of a disk, and then that's probably gonna include radius in it.
Yeah.
And
yeah,
then after we drop that clay, we want to know where it is to change like the the inertia. What's it called? Wasn't there that theorem, parallel axis theorem?
I don't know what that is, but yeah, you're the second person to mention it now, and I don't know what it is, so maybe I should know that.
Maybe.
let's
I don't
see.
know. It's really important. It's basically
Parallel axis theorem just says the moment of inertia around one axis, you know, the moment of inertia around any other axis parallel to it. That doesn't really tell us anything.
Oh, I see. Yeah.
Or does
just
it?
that the mass is not even anymore, and it's not like a disk anymore. It's a disk with a lump.
Mm-hmm.
Yeah. How do we account for that?
Not what parallel axis theorem says. Parallel axis theorem said that if the moment of inertia is parallel to the center of mass, then it's so weird. Then the whole inertia is equal to the inertia of center of mass plus md squared.
So how about we do that? How about we calculate the center of mass, and then we put that as our radius for our moment of inertia.
Like md squared, d is the distance
Okay.
from.
Sure. So if I have this, so the center of mass of that is there, the center of mass of that blob is there. So I'll just take this, just 2 point masses, so and they're all on the x-axis. So the y value is 0. Okay, that makes sense. So the y of the center of sorry, can you say that again? What's the if the center if I center of mass, the inertia on the center of mass is what? md squared? Or
Inertia is parallel to the center of mass, like the line of action, I guess. If the line of action is parallel to the center of mass, then the whole okay, let me just send it to you.
Sure.
I feel like I'll say it wrong and then
No way, yeah.
I'll just put in a discussion.
Like first we need to calculate the center of mass first, right?
Yeah.
So we should do that.
Center of mass.
So 1 over m.
So let's calculate center of mass for the x-axis, and then we can plug that into our equation for the disk, the moment of inertia for a disk, and then we can solve from there.
Yeah, that sounds right. That seems to work for me. How far is it? 1.8. And so that's 1
Is it 0 again?
Because the disk is at the center. The disk itself, the center of mass of the disk. So that cancels. Right, and then, so this is 1 over 32.25. 32.25 times 2.25 times 1.8. So 1 over 32.25 times 2.25 times 1.8. So I got the x value. This is in meters. So yeah, the x value of it is 1.26. No. I don't know why I moved it. 0.126 meters, or I'll just say 13 meters. So that's the center of mass. And so now.
that's the whole cardinal axis theorem, right? Which you just did.
Oh, here, let me. Well, I just found the center of mass, but yeah, let's see what here.
Okay, got confused.
Oh, okay. I have the center of mass. So this is what it says written here. The theorem of parallel axis. I, inertia, which is parallel to some center of mass, is equal to the inertia at the center of mass plus md squared. Or of the center of mass. As a point?
Is that center of mass supposed to be like the larger object or something? Like I didn't.
Yeah, and then this is like there's a axis which is not at the center of mass. So this axis is not at the center of mass, which would be true. Here's our axis. Here's our center of mass. Right? And so that inertia at that point is equal to I of the center of mass. Does that mean just like mr squared? Does that just mean mr squared like as a point?
Yeah, I think it's the same.
You have to take into account the whole turntable. Like the radius is 1.9.
So not just at the point. Not just at the point. The actual whole piece. Like of the actual whole piece here. Plus md squared. So m is mass of the turntable or mass of them together? Mass of them together, I guess. Yeah. I think. And then d
Isn't the turntable half mr squared because it's a disk, or am I?
No.
Well, yeah, that's true. If we're doing a disk, it should be a half mr squared. If I'm taking into account the whole thing.
So shouldn't like the ICM just be like, let's say we're just working with the disk, and then the mass is like the disk with the new mass as well, which is actually parallel to its center of mass times like the distance the new one is squared. Because like this is distance, right?
D is the distance between them. Yeah, it should. Yeah.
So I think that's yeah.
So this 1/2. Okay, so I'll try this. 1/2 m is of them together. So.
Oh no, I don't think it should be them together.
No.
Because like if you look at the thing, it says like IC is just the. It's just I think that's just the original. Because like you're adding the new thing to it. It says like ICM, the initial center of mass, inertia, the original one, plus this new thing, which gives you the parallel.
Would this m be both of them, then?
Yeah, I think so. Like I'm looking at something right now, but I'm not sure. You can try.
Let's try that then. Let's try. It seems to make sense. So 30, 1/2 30 r squared. Oh, but r squared is 0 because distance from. Wait, hold on. No, the radius of the whole disk. Yeah, the radius of the whole disk is 1.9. 0.9 squared plus the mass of them together.
I'm pretty sure you're supposed to use the total mass here. The reason being is that we already counted for what our moment of inertia is with the clay on the thing already.
With the
like,
center of gravity is with the clay on the thing, yeah.
Yeah. So here's what I'm thinking. We have our parallel axis theorem, and what we do with it is we're trying to find the moment of inertia about the center of mass of the turntable itself. So that md squared is just the change of the x center of mass that we have. So we on the left side we treat them as 1, right? And because the center of mass there is slightly offset, right? And we're trying to find the moment of inertia about the middle of the turntable, because that's where we can create an accurate representation of the angular momentum and final angular momentum, right?
Yeah.
the md squared will just be the total m, and then the d, which is 0.13, maybe, I think.
Oh,
To me,
distance from the center.
conceptually makes
Yeah.
sense.
Oh, hold on. Yeah, from the center of. Yeah, this should be. This is between. D is between the axis and the center of mass. 0.13. Yes.
Yeah.
That should be 0.13. Okay. This is. It says ICM. So the inertia as the center of mass. Of the center of mass.
We already got the center of mass to be the total like the clay and the turntable combined, right?
Okay, yeah, I guess so. So 32.25.
If we get it wrong, I guess we can backtrack.
So this would be the IF for the F here, right? So this would be inertia at the end. Yeah, let's get inertia. Inertia to begin with is just for the disk it's 1/2 mr squared. For a disk, I think. Right? So it's just going to be 1/2 31.9 squared times omega I. We know omega I, but I'll just leave it there for now. Equals this, inertia final, times omega F. Okay, so I just divide it. So let's just say 30 times 1.9 squared. You know what, I'll do it just as variables for now, and then I'll deal with it after. So this is just, what did I say this was? 1/2 mr squared, r initial squared. Good, and then so I'll just say omega F equals mri squared omega I over inertia F. Okay, so now expanding this. Mass of the initial bit is 30. This should be a 2 at the bottom here. 30. Then initial radius is 1.9 squared. Omega I is 4.5, I'm pretty sure. And just 4 pi, never mind. All over 2, and then all this. 2 times 1/2, 30, so 32.25, 1.9 squared, plus 32.25 times 0.13. So these 2's will cancel. Okay, let's give it a try. Oh no, those 2's will not cancel. Never mind. Well, okay, I guess they do cancel, and then I'll put a 2 over here. Okay. 30 times something squared times 4 pi, 1.9, and then it's going to be the 0.13, 32.25, 1.9, and 32.25. So I got 11 pretty much. 10.9. For number, what was this number? 25. I think we have the answer in the back. 11.1. So we're 0.1 off. So I think that's good.
I opened it on Chegg. I tried to find it on Chegg, and I think I found the same question. And they really just slid in, what's it called, parallel axis theorem. Like, they didn't really mention anything. It just slid in as the IF, and their IF is half capital M r squared plus lower M r squared. And I think it's just, and the numbers for capital M is is 30. So like that looks like the 30 of the
capital M is just the disk?
Yeah, it's like 30 times 1.9 squared, which is I think it's the radius of the whole disk, right?
Yeah.
And then
that makes sense.
2.25. I think it's just the inertia of like the disk, like the moment of inertia
this
of the
was
disk.
wrong.
Plus,
This should be 30.
Yeah, so I searched it up. So it's like the moment of inertia at the center of mass is supposed to be like a point mass.
That also kind of makes sense. Sorry, go for it.
It was just the moment of the disk. Like, it's like the one you would find in a chart or something, like half mr squared. and then you add to it like a displacement, I guess, mass.
Well, now I actually get an answer that's too big if I do that.
They got 11.1.
The 32.25 is just the mass of the clay, not the table and the clay.
Oh, so then this is the table and the clay here?
No, this is the table, and the second one's just the clay.
Oh, okay. So then this clay was 2.5, was it, or 2.25? Yeah, 2.25.
And then the displacement from the radius, like from the axis rotation too, not the center of mass, or yeah.
So this would be what?
1.8.
1.8? I think we're gonna get an answer that's way too big now, though.
Adam, I sent something in discussions. If you scroll up a bit,
Yeah, I'll take a look.
that might explain what they're talking about.
Still got a number too big. I got 11.7 out of that. Yeah, let's take a look at discussions.
When I did this, I got 11.05 though, the exact same thing.
11.05, yeah. As this exact, so am I just typing it in wrong?
Yeah.
30
I'm not sure.
times 1.9 squared times omega. Wait. Then am I typing something wrong in here? The initial mass is 30, initial radius is 1.9, omega is 4.5. That's right.
I got 11.07. That's fine. I mean, I kind of did it quickly too, but yeah, I got 11.07.
Yeah, I got that too.
Did you multiply the top by half?
Yeah, there's a 2. There's a 2 on the bottom here. There's 2 on the bottom.
Oh, okay.
Yeah, no, I'm typing in right. Is that supposed to be squared? Is that supposed to be squared here?
Yeah.
Yeah, that's supposed to be squared. I didn't square that. Okay, I got 11.07 now, so 11.1 with that. Okay, so now let me correct the numbers here. This was just 30. 1.9. This was just 2.25, and this was 1.8. So let's try to understand what we're doing here a little bit. So the final inertia with the parallel axis is the inertia of the whole turntable itself plus the inertia, or plus md squared. Md squared is pretty much the inertia around the axis of the center of mass, of the other piece. Yeah, pretty much just the inertia of the other piece. Oh, this is just, all this is this is just the disk, inertia of the disk, plus inertia of a point. Yeah, that's all it is. They're not doing anything that fancy here. It's just the sum of the inertias of the two pieces, the inertia of the disk and the inertia of the point.
Yeah, that makes sense. But then, what did you do at the bottom? Did you equate them to each other, like?
Well, yeah. So this piece IF, it goes into this equation, right? So this is angular momentum initial equals angular momentum final, right? So that's okay. Here, I kind of wrote it up here better. So there's that. No, I'll write it out properly. So there. After that, I got I initial omega initial equals inertia final omega final, and then I broke that up here into that. Right? I still have initial, inertia final omega final, and just broke that. We're solving for omega final, right? So I just brought that around, plugged everything in, and I got 11.1.
Wait, I keep getting 11.7 again.
Well, are you plugging in these numbers? Is that squared?
Yep.
Is there a 2 here?
Are you reading it wrong? Is it 11.07? Because I was doing that. It's actually 11.07 sometimes.
I got 11.07.
So wait, why would there be a 2 there?
Well, because this 2, I kind of did it a little too confusing, but there's a 2 being multiplied in the front because it's a 1/2 here, right? It's a 1/2 here.
Yep.
And so I just wait. Is there? Wait, there's a 1. No, it's a 1/2 from here. Sorry, that's where the 1/2 comes from. Yeah, that's where the 1/2 comes from, right? So I just moved the 2 down there, and then it's 2 times IF. So IF is this whole thing, right? But I just multiplied the 2 in to cancel that half in the front, and then so they have to put a 2 here as well. It's confusing algebra for no reason. I should just not do that. So I'll just leave it like this. 2, and there's no 2 there. So 2 times, and then that.
Yeah, it's correct because I get like 1.075.
Yeah, I
and
get
it goes
that.
on. Yeah.
Okay.
Okay.
Here we go. So, there's that one. We only have to do part A for that one, so there you go. And 37 ABCD. 30. Oh boy, where did I go?
So just to recap, we just did angular, like we just equated them, right? And that was it, right?
Yeah, we said the angular momentum is conserved, so the initial equals the final.
We didn't solve for anything before though.
No, we didn't have to solve for any other values. No. We just
Okay.
I just did that.
It's supposed to be negative, I think, because it says clockwise.
Oh, it says clockwise?
Pretty sure.
Oh
my bad. It doesn't say. It's a different question. Sorry.
Different question?
It
Okay,
says
good.
Yeah.
Yeah, there it says counterclockwise. Yeah, good. Okay, we're good. So, okay, next question. This is the last one. What? Oh, it's the first time it's ever done that. I don't know what that happened. So this is the last question from angular momentum before we go to static equilibrium. So, yeah. A rigid massless rod has 3 particles with equal masses attached to it as shown in that figure. Massless rod has 3, okay. The rod is free to rotate in a vertical plane about a frictionless axle perpendicular to the rod that point through the point P and is released from rest in the horizontal position at t equals 0. Assuming m and d are known, find the moment of inertia of the system of 3 particles about the pivot, the torque acting on the system at t equals 0, the angular acceleration of the system at t equals 0, the linear acceleration of the particle labeled 3 at t equals 0. And that's all we have to do, A, B, C, D. Yeah, that's all we have to do. Okay, so, well, first things first, we know m equals m, d equals d. Okay, we know those things. D is, the half the rod. Okay, so the moment of inertia of the system of 3 particles about the pivot. Okay, so, well, of the particles, because the moment of inertia of the about the pivot. So pivot was at P. Oh, I thought it was gonna be right in the middle there. So, is it a massless rod attached to it? So it just it can just spin? Okay, it can just spin. Okay, I see.
I think this is going to be closer to our bonus question because we have to have a formula at the end instead of an actual number.
Yeah, I agree.
It's going to be a similar question.
So, well, do I need the inertia for point masses, or do I need to consider that it's a rod? I guess I need to consider that it's a rod, but it's asking for the moment.
Rod.
What'd you say?
It says massless rod. We don't have to worry about it.
Oh, yes. Okay, so then yeah, we just think about the points. Well, the inertia for a point is just I equals mr squared, right? So let's just add that all up for all of them. So let's say I1 equals, they're all m, and then what's the radius? Well, the radius is d plus d minus 2 over 3d, right? So it's d plus d minus 2 over 3d. Right, so all we have left is from here to here. So 1 minus 2/3 is just a third. So I'll write that a little cleaner here. So it's going to be d plus a third d. Right? Square that. Right? Yeah, and then I can just md squared over 9. No, that's not true. 1 plus a third squared md squared 3/4 squared. So this is going to be 16 over 9 md squared. Okay, that should be the moment of inertia for that point. For point 1 all the way at the end. Okay, so what's number 2? Number 2 is just, so inertia for number 2 is just the distance, right? So, well, sorry, m times the radius. So from the here to here, that's just 1/3 d. So 1/3 d squared. So that's just m d squared over 9. That time it's just d squared over 9. And then I3 is going to be, I3 is going to be m times the radius. Well, it gives us the radius, 2d over 3 squared. So that's m d squared 4 over 9. So 4 over 9 md squared. And just add them all together, I think. So the inertia for the total is just 16 over 9 md squared plus 1 over 9 md squared plus 4 over 9 md squared. So what that is it's 16 over 9 plus 1 over 9 plus 4 over 9 md squared. So 20, 21 over 9. 21 over 9 md squared. I think I can simplify with a 3. Yep, 7 over 3. 7 over 3 md squared. Is that the answer? What question is this? 40? Yeah, there it is. 7 over 3 md squared. Good. Okay, that worked. So that's our moment of inertia for the whole thing.
Could you scroll up a little?
Yeah. So, okay.
How is, like, can you explain why M2, well, at point 2 is 1/3 d squared? We're taking it from point P, right?
Yeah, from point P.
Yeah.
So we're looking for this distance, right? That distance is 1/3 d.
So was the last one? Do we still just, is it negative since it's on this side, or that's just, I'm thinking about?
I think, yeah, I don't think it matters. I don't think it matters in this case. No, because it's like, does mass matter if it's on this side or that side? No, mass doesn't matter. So inertia is like mass, but for angular stuff, right? So you wouldn't say negative mass. So I don't think you can have negative inertia.
Okay.
Okay, so B is the torque acting on the system at t equals 0. So this is where we'll get positive and negative, right? So, yeah, actually, I'll just copy the picture again down here so we have it. Actually, I just want the picture. Okay. So, here we have the torque acting. So there's going to be 3 different torques acting. So there's going to be torque from, do a different color. Torque from 1, which is going to be the distance from the axle times the force, but the only force acting on all these things are just mg, right? Times sine theta. So the forces, all the forces are acting down, and by the same amount. The only thing that's changing is the radius. Remember to mute your mics, guys, if I can hear background noise, just so it's a little easier to focus. So D is going to be, the R here is going to be D plus 1/3 D, right? So is that right? Hold on. Yeah, D plus 1/3 D. So that's going to be 4/3 D. Oh, I did a really weird way of doing that up here, didn't I? Yeah, I didn't have to do that. That was a bad way of doing that. 4/3 D. That's the magnitude of the radius. Times mg, it's just mg, times sine of, well, this is perpendicular, right? So sine of 90 is just 1. So that's the torque done by number 1. Torque done by number 2 is again going to be the distance from the axle times mg times sine of theta, which is going to be the distance from the axle is 1/3 d mg sine of 90. And the torque done by number 3. Oh, and both these are positive, right? Because they're going, this is trying to pull us down like that, counterclockwise. This is going to be pulling us that way, so it's going to be negative. So T3 is going to be the distance from the axle. So distance from the axle times mg times sine theta. So it's going to be 2/3d mg. And I'm thinking that somehow well, it doesn't really make sense, yeah. So sine of 90, but we know this has to be negative. We know it has to be negative, so we'll just make it negative. There you go. Because this is still 90.
Isn't it all rotating counterclockwise?
It's rotating counterclockwise, but this is contributing negative torque, right?
Oh.
This is contributing, like, it's trying to push it this way, right? Which is negative torque. That piece.
Okay.
These two pieces are pushing this way, so they're positive. Right? But yeah, that one's going the other way.
I think the diagram is just kind of displaying that it's gonna be anti-clockwise in the end. So it should be a positive value that we get.
Yeah. The final answer, the final torque is a positive torque. Yeah. Right. So the total torque is going to be 4. Well, I'll just immediately factor everything out. So 4/3 plus 1/3 minus 2/3 dmg. So it's going to be 2/3 plus 1/3, so 1/3. So it's just going to be dmg. Yeah. And we are good. K hat for some reason. Why is it K hat?
B was just asking for it.
Well,
Sorry.
I think they wanted the torque vector. I think that's why.
Yeah. Torque.
B was just asking for
It just says the torque acting on the system, but well, then you just use the right hand rule. See which way is torque going. So it's going, like, you curl your fingers around it, so it's going that way. So torque is coming out towards us, which is K hat. It's my best K yet. Okay. And then, yeah?
Could you explain 2/3? Why is it negative?
So which way is this? Here, let's do it in green. These two are trying to turn the whole rod this way, right? These two are trying to turn it that way from gravity. The torque that's applied is trying to turn it that way. But this one, the torque that's applying is trying to turn it that way, because this is where we're spinning around here, right? So this one's trying to turn it that way. So you just look at which one's the positive. So this is the positive direction. That's the negative direction for torque.
Oh, okay.
Makes sense? Yeah. Okay, so there's that. So then C is the angular acceleration of the system at t equals 0. So to find the angular acceleration, well, what do we know? We know omega 1 equals 0. We know angular acceleration. Oh, I think we can just say the sum of the torques equals the inertia times the angular acceleration. Yeah. So the sum of the torques was dmg k hat. hold on. Why would it be k hat? Let's just say dmg. And then inertia for the whole thing was, we calculated up here, was 7 over 3 md squared times alpha. So m's cancel. One of the d's cancels. So it's just g equals 7 over 3 d alpha. So 3 over 7 g, 3g over 7d equals alpha. Let's see if that's right. 3g over 7d counterclockwise. Yeah, we're good. So that's the angular acceleration. And the linear acceleration of the particle labeled 3 at t equals 0. Well, don't I just do r times the angular acceleration? I think I do. So t, the tangential acceleration for point number 3, yeah, 3 equals r alpha, or r3 alpha. So r3 is 2 over 3d, and alpha was 3 over 7 g over d, g over d. So that's going to be, the d's are going to cancel, so it's going to be 6 over 21g.
Is this a part of C or D?
This is part D. This is part D.
Velocity negative for this one, because it's going the opposite direction.
Isn't it 2 over 7? Because you can cancel out the 3's.
Yes.
Right.
Yes. 2 over 7. Although it's the same thing, but yeah, you're right. You can cancel the 3's. And I got 2 over 7 g upward, yeah.
Oh.
So that's, oh wait, upward. Why is it up? Oh yeah, upward, because this is going to start going up. This point is going to go up. Right? Because it's spinning that way, so it's going to go up. Okay, well then that is chapter 11. That's angular acceleration. Let's move on. Unless anyone has any questions for that, let's move on.
I do have one question.
For sure.
So like, does it matter? Because like for part B, when it says to find torque, does it matter that they gave us a specification of time is equal to 0?
It just means that this is what you're looking at. They're looking at this picture.
Oh, okay.
This is time equals 0, so just use this picture for reference of what's happening. Yeah.
Okay.
That's why they say that.
Okay.
One more thing. D, can you scroll down? Like last, yeah. Okay, so like G would be the linear acceleration, and then D is just the radius. Okay, cool.
G is from like just the force of gravity. It's like the 9.81,
yeah.
Right? 9.8
yeah.
acceleration due to gravity. And this is our linear acceleration.
Yeah.
Okay, I'll find the next problem. So the next problems start at number 6 in static equilibrium. Okay. Okay. I'm gonna take off my sweater. It's hot here. Just take it off. Okay. What am I clicking? Okay, good. So, this one is number 6. There we go. So, a uniform beam of length, let me make sure this is the right question. Number 6 from static equilibrium, yes. A uniform beam of length that and weight that is carried by two workers, Sam and Joe, as shown in that figure. Determine the force that each person exerts on the beam. Okay. So, okay. That whole distance is 7.6. What'd you say?
Oh, no, sorry.
Maybe not to me. Yeah. Okay. This person's 2 meters from the end. This person's 1 meter from the end. The force of gravity acting downwards, right, is 4.5 times 10 to the 2 newtons. Okay. Carried by the two workers, Sam and Joe. There. We know that it's not. So first of all, they're all 2 meters from the end. Okay. So if they were both right at the ends, I think they would just, or if they were equal distance from the ends, they would just be each holding half the newtons, right? Or if they were each equal distance from it, they'd each be holding half the newtons of it. But since they're not, the sum of their forces has to be that still, right? But the amount that they each individually do is going to be different because we have two positions of like torque here. So what's the torque, or no, hold on. Where would it rotate from? We would just say the middle or the end. I think we can choose anywhere actually.
You can choose anywhere.
Yeah, so let's choose here as that's where the torque is going to be calculated from. Okay, and so we can say the sum of the torques is equal to 0 because it's not rotating. Well, what's the sum of the torques? Both of them are they're both applying a force upward, right? So they're both their applied force, because to hold it up from gravity, they're both applying a force upward, right? So I'll call this one, well, this is just like torque from Sam, torque from Joe. Okay, so let's figure out each one. So torque from, okay, first of all, let's actually figure out if they're positive or negative. So if this person's torque is upwards, it's trying to pull it that way, so they're both positive. So it's just a torque from Sam plus the torque from Joe equals 0. Does that make sense? Well, let's go forward. Let's just calculate the torques and then we'll see what happens. So torque from Sam is his distance.
Would you also include the mg, the mass, on the negative direction?
Where would I include it? Here? Well, but this is just the sum of the torques. We're just doing the sum of the torques on this side.
Okay.
Right? This side would have, this side would have inertia times angular acceleration, but that's 0. So that's why I just go right to 0.
Okay.
No, I think he might be like just at the weight, because the weight is gonna produce some sort of torque, right? Like if you just hold something.
Oh, yeah, you're right.
Okay,
There is going to be a torque. Yes, you're right. There is some sort of torque happening there. Very good point. So this will be negative direction. It's going to be minus the torque caused by the mass equals 0. Good.
Okay.
So the torque caused by Sam is his distance from the axle, times the force that Sam is applying, right? Times sine theta.
Quick question.
Yeah.
Do we have to worry about like clockwise and anti-clockwise, like Sam being on the far left? Does that mean he's going clockwise? And
well, notice which ones are positive and negative here. Right? So these guys are both, the force that they're applying, the torque from their force that they're applying, is trying to pull the whole thing that way, right? They're pulling up, so it's as if it's rotating, trying to pull it that way. So the torque is positive. This one is trying to pull this down that way, so that's a negative torque. This force here, that's a negative torque. Okay, so his distance from the beam is 1, so it's 1 times the force done by Sam, or the magnitude of the force. Well, I'll just call it Fs, but it's the magnitude, times sine of 90, right? So that's it. So that's just Fs. Torque done by Joe is going to be his distance from the axis, the force done by Joe times sine of theta. So his distance from the axis is going to be 5.6, right? 7.6 minus 2. 5.6 times the force done by Joe. Sine of 90 is 1, so that's the torque done by Joe. And now the torque done by gravity.
Wait, why isn't Joe's negative?
Because he's pulling up, right? And here's their, that's what we're spinning around, this point right here. We're saying we're spinning around, right? So if he's pulling up, it's trying to move this whole piece like that. Like if it were to move, and these guys, the other forces didn't exist here, right? Then it's like if he were to just pull up on the beam and it rotated around here, the beam would rotate like counterclockwise, right? And so that's positive torque. This is positive torque, and this is negative torque. So yeah, gravity's doing negative torque because it's trying to move it. If you were just spinning around here, gravity would make it fall down like that, right? And it would hang like that. So that's doing negative torque because it's pushing in this direction. Does that make sense?
I don't know. I think I'm doing the right hand rule wrong.
I honestly, I don't even think about the right hand rule with this. I just think about which way would it move. If there was no other force acting on it, I just had like a pin here, and just this force acting, which way would it spin? Which way would this rotate? Well, if it rotates this way, it's positive. If it rotates this way, it's negative.
Oh, okay.
Yo, I have a question.
Yeah.
If we're trying to find actual numeric values, well, we need to like relate the fs like as in like a ratio, because like if we have fs and then fj or whatever, we'll still have two unknowns. Are we trying to find the actual values?
Yeah, we are trying to find the actual values, and we'll find it. There's still more to go, right? We're not quite there yet, right?
All right.
So what's
Think of it like
the
calculus.
value
When you ever
here?
do calculated radians and like an angle, counterclockwise would be positive and clockwise would be negative. Same thing here.
Yeah, someone's gonna say something, Ronak.
I want to add something like how is it called the instrument for doing circle? Circle.
The compass?
Yeah, the compass. If you put one part of the compass in the center, and then you follow the
way it
force,
would spin. The way it would spin. Yeah.
you see the way we spin. I don't know if it help you visualize.
Right. If you put a compass like that, and I draw the other end of the compass like that. There's the pencil, and then there's the pin, and you follow the force. That's the direction of the torque, and that's the negative direction. Right. That's the negative direction.
Wait, is the radius in the middle or at the side?
The where we're rotating around is right here, the side, right here.
Oh, okay.
I chose that as the axis. Because the distances are measured from there pretty much. So, yeah, not the middle. We're not rotating around the middle. Yeah. So that would So
what's the theta value here?
Theta?
Yeah, what's theta?
It's all 90. They're all perpendicular.
Oh, okay.
They're all perpendicular to the line of action. Yeah.
But the torque in the center is 0, no?
Not quite 0 because it is a force. There's a force acting here, force of gravity, right?
Yeah, but it's not 0.
No, it's not. It wouldn't be 0 because here, look, torque is going to be the distance from the end here. Oh, okay. The reason you think it's 0 is because you're imagining that we're spinning around here as if it's going to spin like that, right? But that's not the case. We're spinning from the end here, so it can only spin either like that or like that.
Oh.
This point stays fixed in place. So if gravity was acting here, then yeah, that would be 0. But gravity's not acting there.
Okay, I thought they were moving it around the road. Instead, there is a pivot there.
Yeah, the pivot. I put the pivot there. I put it there.
Okay.
Which might have been a confusing move, but I think it simplified some of the calculation of distances.
I may be wrong, but I think I remember them talking in the lectures and stuff that sometimes you want to choose your pivot point to eliminate the most amount of forces, because then it's like getting rid of a lot of variables. and
Yeah.
you can solve for stuff a bit easier. If
That's
we put
true.
it like
So
about Sam or about Joe, then we wouldn't have to solve for them, and we would have like a thing to plug in right away. But I'm not sure if that's gonna matter for this question. I was just gonna see like, I don't know if like if we have like net force equaling to 0, and it would still be able to. We'd have enough variables and enough equations and everything.
yeah, let's see. Yeah, if I have trouble, I can't find anything. Yeah, that's very true. I probably should have put it on one of the forces. So yeah, I would put it on like Sam or something, right? And then yeah, that might work if we're out of like variables. So then this is just the force done by gravity, which is just mg. Oh no, we know the force done by gravity is exactly that. So I'll say that equals, I'll just say equals W, the weight. So it's just W sine theta. So it's just the distance, so that's just going to be half of that. So 7.6 divided by 2 is 3.5, 3.8. Make sure, but 7.6 divided by 2 is 3.8. Yes. So 3.8 W is the torque done by gravity. So yeah, we're going to have one equation. We'll also have, the thing is that we'll also have the sum of the forces. Yeah, we'll also have like the sum of the forces in the y direction equals 0. It's not moving in the y direction, right? And well, look at the forces. We call this our positive direction, so it's going to be the force done by Sam, force done by Joe, minus the force of gravity. Force done by Sam plus the force done by Joe minus the force of gravity. Well, I'll call it weight equals 0. Right? So now we have two equations and two unknowns. Well, we will in 1 second. So there's our first equation, and our second equation is just I put in these torque values into here. So the torque done by...
How did you get 3.8? Sorry.
Just divided this by 2. Because you see it's...
But don't you have to multiply it by the weight as well?
Yeah, 3.8 times W.
Oh, okay.
For the, yeah. So I just left it as 3.8 times W. Don't worry. So TS is just, so the torque done by Sam is just the force done by Sam, plus TJ is 5.6 times the force done by Joe, minus the weight, minus the torque done by the mass or by gravity, and that's going to be 3.8 times W, and that equals 0. So we have two equations, two unknowns. We can deal with this. So I'll take, well, I want to put it in a matrix, but we won't do that. So this is going to be Fs equals W, shouldn't be W like that, should be W like that, minus the force done by Joe. Put that into here. Yeah, that's a J, by the way. I know it looks like an S, but so W minus the force done by Joe plus 5.6 times the force done by Joe minus 3.8 W equals 0. Not bad. So it's going to be 4.6 times the force done by Joe minus 2.8 times the work equals 0 times the work, but the weight. So the force done by Joe equals 2.8 W over 4.6. W, remember, as they gave us in the question, is the weight, so 4.5 times 10 to the 2. So 2.8 times 4.5 times 10 to the 2 over 4.6. So I got 273.9 newtons. And now we can just go back here to this equation, right? So it's going to be the force done by Sam is equal to whatever I said, 4.5, well, the weight, minus 273.9 newtons. So that's going to be 4.5 times 10 to the 2 minus answer. So I got 176 newtons. Let's see if that's right. We don't have the answers for this one, I don't think. We don't.
I got the same answer.
Okay, good.
But I did it in a different way.
Well, that's a good sign that that's the right answer then. Right.
Yo.
Two different ways. Yeah.
Yeah,
Can you
I
like
got the
What
sound
was the
setting.
weight again? Can I see what the weight was? I just.
Yeah.
Okay.
Okay, thank you.
Yeah, so the first equation was just the
Here?
right. No. What was the first equation? Wasn't it the force?
This
The
one
two
was the
forces.
forces in the three forces in the y direction.
Okay, and then the second equation was the.
Torques was the torques.
So why is it? I see you have S F and forces twice as two different equations.
Where do you see? Here I have.
Yeah.
Yeah, here these
Right.
ones.
Yeah.
That comes from the torque. So look here. So Fs is Ts, which we said over here was using this. We said Ts was Fs, right? And then the next one, Tj, we got here was 5.6 Fj, which is I put 5.6 Fj, right? And then minus Tg, we did over here.
Yeah.
3.8 times the weight, minus 3.8 times the weight.
But the second one is the torque, and this first one is the forces in the y direction.
Yeah, exactly. This is the torque. This is forces in the y direction.
Okay, and then we just equate them. Well, we equated the simpler one to get one variable.
Yeah, just solve the system. Yeah, just solve the system.
Cool. Thanks.
No problem. So yeah. Okay, so there's that. There's that question. Let's keep going. So next is what is next? 7. So here find the mass m of the counterweight needed to balance a truck with that mass on an incline of theta. Assume both pulleys are frictionless and massless. Okay. So, we need to figure out this mass here. Oh, wow. Okay, so it's a complicated, like, not pulley, but the complicated, pulley. I guess it is called a pulley. Oh, yeah, it is a pulley. Never mind. I was going to call it like a wheel, but no, yeah. Complicated pulley going. There's 2 of them. Oh, boy. Okay, so what do we know? We know this mass is 1,500 kilograms. So this mass, sum of the forces in the. Okay, what's the sum of the forces in the y direction? Let's start with that. So it's probably gonna end up just being find the sum of the forces in the y direction, sum of the forces in the x direction, and solve like that. So the sum of the forces, yeah, and torque, yeah. So sum of the forces in the y direction, we have a force acting here, force acting here. That's it. So,
well, how about the tension force acting on block M,
yeah,
the small m?
Yes, that's true. Well, there's tension force going up like that. So I'll have to do it separately for separate pieces. And then there's also this tension force. There's a double pulley here. Oh boy.
So it's 2T then.
Yeah, there is a double puller.
But like when one is attached, does that still doesn't it just have the equal amount?
Yeah, it should be the equal amount. So it should be 2T then.
Yeah.
Yeah.
Okay, so then now let's just focus on this first. Well, let's do this one quickly. It won't take very long, right? So it's just the force of tension. Yeah, the force of tension, and this is the force of gravity on on M, right? So this is just if I say, which I say is positive. I guess I'll say. That is positive, right? So y, x. So it's going to be F, G, M. Or is that confusing? Should I just do normal? Should I just do normal axes, or what do people think?
Are you just solving for tension in M, which is going to be equal to the tension over the other side? What are you doing right now?
I'm just solving for the sum of the forces in the y direction for this one, so that I show that FGM equals FT for this piece.
Yeah.
And then for this one, I'm going to do the y direction as well. So there's no sum of the forces in the y direction here, right? So sum of the forces, there's no sum of the forces in the x direction here. So sum of the forces in the y direction is, well, it's going to be gravity. So this is the force of gravity on the bigger mass. So FGM minus the force of tension force of tension cos theta. So 2 times the force of tension cos theta. Right? So we have 2 forces of tension going up. 1, 2. Right? Each of them has a magnitude of force of tension. But since we're in the y direction, we're in the y direction, so it's sine theta. I thought we were in the x direction. So it's going to be sine theta, right? Because we want opposite over hypotenuse, right? Opposite is the y direction. Opposite over hypotenuse, x direction will be cos theta. So that equals 0. And then once again, sum of the forces in the x direction this time is also 0. So what's the sum of the forces in the x direction? Good. So it's going to be...
Is it muted? I don't know.
Oh, I forgot the normal force, didn't I? There's a normal force here. Like that. Yes, I forgot the normal force. And so the normal force, let's call that theta. Because right now this should work. Although that doesn't... Fn. So,
how do you know the tension in the smaller pulley and the bigger pulley is the same?
Because one string. It's one string. So always if it's one string, then I think it's the same. Oh no, hold on, it's not one string between these two. Wow, hold on, there's a complicated pulley thing happening here.
Yo, I don't think it's just me.
But I'm not sure if other people can.
I can't hear. It's just like...
Can
you guys hear me?
I can hear you, yeah.
I can hear you now, but like not for the last minute. So like, can you start back from 2ft sine theta cos 0?
I can still hear the...
But who, like, what are you watching my stream or are you watching the second stream?
On your stream, so yeah.
Oh, really? But
Yeah.
How many people are experiencing that?
I was watching the stream and it was perfectly fine for me.
I was experiencing some of that.
Yeah.
So it might be Discord.
Yeah, it's completely cut
then.
out for me.
It might be Discord then, because...
Yeah.
It's probably just Discord since there's a ton of people.
Yeah.
Discord probably gonna start tracking this file. They're like, nah, too many people.
Yeah.
Discord.
So, okay, let me get this going here again. Sorry. Okay. So, so what was I saying? Here, some of the forces in the y direction for this one. What other forces acting on it? Well, we have the 2 forces of tension going up, right, and sine theta. That's our theta. I forgot the normal force. Is there any other forces I'm forgetting? Normal force, force of gravity, force of tension. No, I think that's okay. Force of tension.
Isn't force of gravity at like an angle for inclined? Because it from your oh no, never mind. You put your
axis like that. Yeah. Which maybe wasn't the best idea, but it's okay. Honestly, it's not going to cause any problems.
Personally, I'm kind of confused on like what we're using which ones are we using the angles for? Like to get components?
Well, anyone that's on an angle, right? So F of t is on an angle. Sorry, force of tension is on an angle. This force of tension is not on an angle. This force of tension is not on an angle. Force of gravity is not on an angle.
Why would it be 2ft again?
Yeah, here 2ft. I have 2ft here.
Why?
Because there's
there's 2 ropes there.
Yeah, it's like it's going on both sides of it.
And then that 2ft would just equal the ft that's on the that's equal to the.
No, it's 2.
Or it's just straight up 2ft.
Yeah.
Okay.
Side tensions are the same, but when for some rule where it's like if it's attached to a fixed area, it's like counts as a second tension.
Okay.
Yeah, it does. I don't fully understand it either, but it's just like a rule that I just apply here. What I'm kind of confused about is, are these 2 strings attached? Because look at what's happening here. It's going into a smaller radius, and then there's a bigger radius of that circle. So let me see this. Find the message.
No.
They just have separate torques.
Right. With this too, there's like 3R and then there's R. I didn't even see that.
Right, so it's two different wheels here. There's one smaller wheel and one bigger wheel. Right.
Wow.
So they're,
Can I suggest something? Maybe it's better if do a system of equation. Just put it there, like the one in mass. The
well, that's what I'm trying to do.
like, for example-
I'm trying to make a system. Like I have this equation, I'm making another equation. Right.
Okay.
So they gave. Yeah. Go ahead.
What do we do?
And then the second one is for the torque.
Yeah,
So-
we'll have a couple. We won't just have two. We'll have a couple. Yeah, we'll like a few more than that. Yeah, but yeah. So we'll also do the torque. That'll be the next thing though. So first, I'm doing just the forces here. Yeah. So, then I missed something here because there's that. So that force is acting. So the y component of that is going to be Fn, so plus Fn cos theta. Like
It's
that.
not frictionless. Or there's friction.
It is frictionless. Yes, pulleys. Assume both pulleys are frictionless, and well, this says pulleys, but it doesn't tell us anything about friction, so we have to assume it's frictionless. Yeah. Well, actually, sorry, it's also not moving, so it's also not moving.
Okay.
And that equals 0. Okay, so we have another equation, two equations. Now, some of the forces in the x direction. I honestly should have probably put my axes on the diagonal, but then this would have been more complicated too. So, anyways, that equals 0. So what's happening in the x direction? So we have pretty much nothing. So we got to do some other things here. So nothing directly in the x direction. So this is going to be 2 ft cos theta. And then this is going to be minus Fn sine theta.
Wait, what about didn't you say you broke the normal into two components?
Yeah. So Fn sine theta, Fn cos theta.
Oh. Okay. Yeah, sure.
I'm so confused right now because did you just combine the forces from both of the masses?
No, this is just for here. This is just for here. Should use a different color. This, it's only in the y direction, is just for here. And so
I see.
that goes there, and then that.
I have a question. Why the Fn cos theta is positive and not negative?
For Fn cos theta, it should be negative. Should be negative. Yeah, because it's going up, which is the negative y direction. Yeah.
When FGM and Fn cos theta cancel each other out.
This FGM and Fn cos theta. Yeah. Yeah, I guess they would. Let me think for a second. But hold on, we also have not quite, because we also have this.
Wait, isn't there acceleration in the x direction?
I think you made a mistake here. Okay, maybe this is just your way to solve it, but personally, I wouldn't change the axes here.
You wouldn't?
Like I would like for the green portion of it, you would just keep the slanted axis.
Yeah.
Yeah, I understand that probably would be simpler, but then I can't have two different axes, can I? For two different parts, I can't say this. No, I think I have to say.
You can say
but the FT there is just equal to the FT in this on the slanted. You're just breaking into components.
You can put x parallel to the plane.
No, I understand. Yeah, I understand that. So, okay, and then this wouldn't change, right?
Yeah, that wouldn't change. That was
okay.
No.
Okay, as long as that wouldn't change, then sure. Okay, so we'll just erase this, and it'll be simpler if we do it like that. Yeah, that's why I didn't do it, because I didn't know if that would change or not. But I guess that makes sense because it'll always be equal. those magnitudes will always be equal.
Yeah. Like if the FT is going upwards, that should be matched with the FT that's on the slant.
It should be, but again, we're on two different pulleys here. They're two different strings. I don't think it's the same force of tension. But then wait, hold on. How would that?
That would be
But
weird.
yeah, it doesn't have to be the same, but accelerations are related.
Yeah.
Because they gave us radius, so the accelerations of each mass are related somehow.
But that one, you can, the force of tension will resolve when you calculate the torque, when you put the third equation. Until now.
Yeah, when I'm at torque. When I'm at torque, I know. Yeah.
Are we solving for torque as well? So maybe that's when the radius comes
Yeah, that's
in.
when
Like,
that's when that comes in for sure. For sure, that's when that comes in.
Are we given the radius?
No,
They just call them R. They just call it R. 3R.
Okay.
C, R, and
I'm
R.
guessing it probably cancels out in the middle or something.
Yeah, so I'm thinking. Okay, so now with this, I will just say, okay, so some of the forces in the x direction equals 0. So it's 2ft. Should call them different FTs though. To call them FT for the big mass. Then there's what else is going in the x direction? The
force of gravity is the only thing that you need to convert into.
Would it be Fn sine theta?
Wait, are we sure we're gonna label them differently? Because aren't they supposed to be like the same as FT on the other side?
It is, right?
I don't think they're the same thing in this case again because there's two different pulleys. I think they're two different strings.
Yeah, I think that would differentiate them.
Yeah, they're two different
Because
strings.
one's coming out from a larger angle from the center, and I think that would have like a change on the.
I think so.
There might need.
How would you find what that second string is?
So you're solving for
You
the
can
X.
put FT1, FT2. Oh, it's okay.
Well, I just put FT capital M and then FT lowercase m or FT lowercase m.
There's nothing relating to that second string. How do we find what that second string is?
With the torque.
Because we still don't know.
The torque is what's going to relate them. With the
the torque will also work for the second pulley?
Yeah, they're related. I mean, the wheel is going to spin. The wheel will spin. Oh no, will the wheel spin together? I think it's one. The wheel will spin together. We don't know a lot about that wheel. That's the.
The wheels would definitely have to be on the same axis, or it just wouldn't work. So they're definitely spinning.
They're definitely going to spin together. Yeah.
Okay. Can I see the question again? Can you scroll up for a second?
Yeah.
Thank you.
I think like the pulley system's unclear. I doubt it'd be like that bad on an exam.
Yeah, no, I don't think so. Yeah. Okay, so what else is in the x direction? There's going to be What was it? Sorry.
The second string.
Well, it looks like this is one string, and this is a different string. Because this one is going into the small wheel, and this one's going into the big wheel.
And here you need to use.
Dude, unless it's like a coil.
Right hand rule to see that there's a force inside.
So I tried something and I got the answer. So what I did was, so I calculated the net force in the x direction like you did, and the tension should be the same for both.
Oh, okay.
And then so it was big mg sine theta equals to 2t, right? And then what I did was I found the tension, and then for the small mass that we're trying to calculate, the R is 3R, right? So the torque is basically the force times the R, right? So I did the tension times 3R, and that gave me the answer.
Okay.
And I just isolated for M.
So you treated the tensions as the same. You treated the tensions as the same on both sides here.
Yeah.
Okay, and since I got you the answer, that's the right thing. But I don't get how that would work though, because how could that be the same tension if it's this?
It may be because it's the same string.
Maybe it's the same tension
But
after the whole.
how look at the geometry of it. How would it be the same string? There's one going like this. Would it then somehow go
Oh,
to the.
no, it might be
Yeah, I'm
going.
saying that maybe it's
Something might have
coil and the
rotated
tensions that are
around.
there are like
It's gonna be other
after the
one.
application. It's not like
Hold on. Too many people talking at the same time. I didn't hear anyone. So one person. What was?
the person who was talking first can go.
Yeah. Whoever. It doesn't matter who. Just. Okay. Then.
I was just saying that maybe tensions are the same because like it's after the radius and thing. Maybe it's just like it's just equal. I don't know.
Okay.
I think you're just overthinking it, to be honest.
Okay. Okay.
I'm checking
Like
DM.
equal to be like right.
Yeah, like I think the tension is the same because it's frictionless, massless. But I'm not sure if that's correct. I just did that and I got the answer. So I don't know.
Okay, well let's just keep going here. Let's keep going. So the x direction, this is going to be minus that's theta, so it's going to be minus FG for the bigger mass sine theta equals 0. Okay. Then I don't really need the y direction. I don't think there's anything that's going to help me there. Yeah. So I just have 2 FTM equals F FGM yeah, no, sorry, didn't mean to erase that. FGM sine theta. And so I'm trying to solve for this mass, right? The smaller mass. So if I just turn this into, if I say these are equal, right? So I'll just call those FT. I know both of these now. And then this FG small m is just small m. It's just small mg equals ft. This one is 2ft equals big mg sine theta. Isn't that enough to solve for small m?
Yeah.
Yeah. Can't I just, okay, I think I can just say 2mg equals mg sine theta. G's cancel. And so I'm solving for the little m, so m equals big M over 2 sine theta. Big M over, okay, hold on, someone's knocking at the door. 1 second.
Can someone just explain to me in the meanwhile why it's FG sine theta? Like I'm not really getting the angle.
FG is just the force of gravity of the truck, right? And sine theta, all we're doing with the sine theta is making it in the slanted axes that we chosen.
We need the x component.
Right? With the
so if we chose cos theta, it would be the one that's perpendicular to the plane, and that would just be canceled out by the normal force, so we're not taking that into account. And then the one that's going straight down is going to have a component in the x direction, and that's the one we're taking care of, and that's the one that's sine theta.
I think I get it, yeah. Thanks.
So is the answer 530? Oh no, it's here right here. It's here right here. Yeah. Okay, so no, not what I got. Hold on. What did I do differently? It's 1,500 kilograms.
You isolate for T. You don't like do the mg part for tension.
Isolate for G?
Or isolate for T, like force of tension.
Yeah, here. I isolated force of tension here.
Yo, the tensions aren't equal. That's why you're getting the wrong answer.
Oh.
So what you need to do is...
That's what I thought, yeah. So
what you need to do is... So you have the pulley, which are like connected together. So you have radius of 1 and then radius of 3.
Mm-hmm.
And those equal to 0.
The torque
as a net torque.
Yeah.
And then you have to basically rearrange, and then you get that the tension on one is equal to 3 of the tension on the other.
Yeah. Okay. That makes But
so it will be m over 6, not m over 2. Yeah.
Yeah, that's what I was thinking. But someone else said that they treated the torques the same. They treated the forces of tension the same, and they got the right answer. They said the two.
Yeah. If you do treat them the same, I even got 177 as well.
Yep, I got that too, but I did a different way.
You just forgot to include the 3R.
Which means that the torque, it's different. The tension's different. if you're
I know, but
keeping it 3.
yeah, I agree. The torques, the tensions should be different. I initially thought the tensions should be different, and they seem like they should be. But people are saying they did it with the torques, the tensions being the same, and they got the right answer.
Then write it with a torque equation.
Can somebody
Something.
write that out though? And can someone send their solution like in the group so we can see something?
Just write 3r times the force of tension sine theta, and then solve for mg or solve for m. Isn't that what they're saying?
I think you guys are just confused where the 3 is coming from.
No, I get where the 3 is coming from, but like I'm
So-
asking if that's what you mean we should do.
I think we can do a better analysis if we do it just with torque.
Yeah,
So if
I
we
was gonna
just-
do torque
because-
now too. Yeah.
So let's just forget about the forces right now and just go with torque, because since we know it's in equilibrium, we know that the torque that the tension is providing of the counterweight is going to be the same torque that the other ones were applying, right? So we can set it equal to 0 and set them equal to each other, and we have most of our information. Not most, but like I think we can get most of our a bunch of our information.
This is the force of tension done by the smaller mass. This is the force of tension done by the big. Oh, sorry. No, I did it the wrong way. This is the smaller mass. That's the bigger mass. Okay, that's the bigger mass there. So the force of tension done by the torque done on this wheel by the bigger mass is going to be positive, right? So I'm going to call that the torque. The torque done by the bigger mass minus the torque done by the smaller mass equals 0. Okay.
Mm-hmm.
Now the torque. I'll rearrange this one more time. So I'll just say this equals this. Okay. And so now the distance from the axle for the torque done by the bigger mass is r. Okay. So I'll write the full formula first though. Magnitude of r times the force times sine theta equals the r times f times sine theta, but they're different. So this one's r. This is the force of tension by the bigger mass, and this is sine theta, the same theta, I think. Yeah, that's theta. Yeah, that's just theta, I think. No, is that 90 minus theta?
Adam, I sent you my solution in your DMs, so maybe.
It's just theta because it's got this black.
Guys, can you let him finish? Because if not, we.
Okay. So, yeah, let's keep going. So 3r, the force done by the tension on the smaller mass, times sine theta. This is a different theta, though. So this is sine phi, right? Because this is just 90. There he is the 90-degree angle there, right? But here, this is theta. So that's just sine of 90. The r's are going to cancel, right? Force of tension. Okay, so F T big M sine theta equals 3. Force of tension on the small mass, is equal just to mg, small mass times g, right? So this is just mg. Sine of 90 is just 1. So we're solving for this, right? So this is going to be the force of tension on the big mass times sine theta over 3g is the small mass. Now we just got to figure out that force of tension on the big mass. So the force of tension on the big mass is going to be the sum of the forces in the x direction is equal to -2 force of tension, +2 force of tension on the big mass minus force of gravity on the big mass sine theta. So just this divided by 2. Fg big M. Why did I switch that to big M? Oh no, that makes sense. Never mind. I don't know why I'm saying that. Yeah. Okay, so then we have this, right? Put that in here for that. So big Mg sine theta over 2. Big M G.
You can call it sine in a different sine 1 or something, because they are 2 different angles.
These thetas are the same, I think. These thetas are these thetas are the same. That theta and the theta from our torque is the same. This case, they're the same. Yeah.
That theta is also the same because we have a 45-degree angle.
Yeah. All these thetas are 45 degrees.
Mhm.
Over 3g, right? I don't know, I wrote it so separately like that. 3.
Why would you do over 2?
Because it was 2 times the force of tension, because there's 2 forces of tension because the 2 pulley things. Right?
Oh, okay.
Right?
Those divide the force.
So yes, then since there's 2 of them, you just divide it by 2, so you get the force of tension. Oh, force of tension on the big mass. So now these g's should cancel. I just flip. Yeah, these g's should cancel, I think, and hopefully. And then this should be big M sine squared theta over 6 equals little m. So 1500 times sine 45 over 6. I got 125. So not quite the answer. Maybe just some of my algebra is wrong here.
It's not sine squared theta, it's just sine theta.
Why though? What are the 2 signs here? I have a sign from this.
So,
a sign from this.
Well, why'd you put the sign up here?
Of this one?
It's supposed to be.
Yep.
This one from from the torque.
It's still 90 degrees.
Still 90 degrees, right?
It's still
because
90
it's still going to
degrees.
be, yeah,
one-
it's
one-
still going to
1%.
be perpendicular
Oh,
to, like, if you look at the pulley, right?
Yeah.
And the pull of the rope, it's still going to be 90 degrees to the surface. to the
Oh,
rim.
you're right. Yep, you're right.
So that's where the sign kind of got doubled
yep,
up.
this got put away, gone. So now
You should get the right answer.
Now I'm supposed
176.7 or 1.76.8. M equals
That's the right answer.
176.8.
Yeah, that's it.
Okay. So the question isn't actually that bad because like once we started doing it, it's not that long, right? But yeah, to understand what's going on here for sure, that took a little while. So this, I'll do a recap, even just, well, let's just figure it out. So start with the torque. That's probably a better way to do it. Start with the torque, right? So the torque that's happening on these guys is 0. So the torque done by the big mass is equal to the torque done by the smaller mass, because that's the only 2 torques that are happening, right? Torque done by the big mass is its distance from the axle times the force times sine of that, the distance between those. Both of these signs are sine of 90, so they both go away. So actually, I'll even put that as that for both of them. It's just 90. And then, because they're not theta. So then, same thing here. Distance from the axle, force, FTM, right? So it's just here, all we have left, the R's cancel. So it's the force of tension on the big mass is equal to 3 times mg, because the force of tension on the small mass is just equal to mg, because that's what we found from the sum of the forces in the y direction here, right? Force of tension on the small mass is equal to mg. So we rearrange it for small m. Then we just need to find an expression for FTM, right? For force of tension on the big mass. That's where we use our sum of the forces in the x direction here. 2 times the force of tension on the big mass minus the force of gravity on the big mass sine theta to get the x component here, right? Equals 0. Let's rearrange for FTM, force of tension on the big mass. Plug that into here. Solve for m. Well, it's already solved, but just plug in values. Okay. So not that bad. That just took us a while to figure that out. But yeah, not that bad.
How did you know that the radius for the big mass was just r, not 3r?
Well, it shows here where the string is attached, right? So from the middle to here, it says r. It says r there. That radius, that smaller radius is r, and the bigger radius is 3r.
Is the force of tension going to the outer wheel?
Well, one of them is going to the smaller wheel. So this force of tension is going to the smaller wheel, and this force of tension is going to the bigger wheel.
Oh, okay. I see.
Right, yeah. Okay, there you go. That's that question. I wonder how long that took. We'll see in the recording. Let's see. Let's keep going. So that was number 7. So number 11 is next.
I have a general question.
Sure.
Is the torque ever not 90 degrees?
Yeah. It is sometimes. So again, if I have like a clay wheel, like a potter's wheel, and you're spinning it, and it's spinning this direction, right? And I apply a force, I push with my finger like that, or kind of like that, right? So not perfectly straight down on it, not perfectly that way on it, right? On some angle theta, right? Well, sorry, the angle theta would kind of be like that, right? That angle theta, right? So then if I figure out what angle I want for my actual torque, well, I have to figure out the angle between this vector and this vector. So that would be that theta. So that's not theta actually, but that's just the angle, right? So if I'm pushing on some angle there, then that's theta, which wouldn't be 90.
Wouldn't this be a friction example again? That friction would always be perpendicular.
In this case, my actual force is causing torque. My actual force. It's not just friction causing torque, right? So friction would also be causing some sort of torque, I think. Yeah, well, it must be. So if it's trying to move this way, so then, yeah, friction would also be causing another force, and that angle would be 90. But my actual pressure, the actual applied force I'm putting, is also causing a torque in this case. Not like if I were to take the wheel and it's spinning this direction, and if I were to just press straight on it, my force would not be causing torque, but the friction caused by my force would be causing torque.
Wait, so natural causes, so things that are not applied forces, would always be tangential to the thing?
I don't know
Something
about
like
always, but let me
friction?
think. I can't think of an example where it's not. Yeah, friction is tangential.
And then
So
we also
sine
had that
90.
previous example where the tension of the rope was tangential as well.
Yeah, for sure. That one would be just because of the geometry of it, right? Just because of like how it pulls on the wheel, right?
Mhm.
I can't think of an example where it's not, but it's better to just not think of it as a rule and just like look at the picture, right?
Okay.
Decide from there. Okay, so the next part.
This one I couldn't get. I didn't understand it. I tried it yesterday, bro.
Well, let's see how we do. Two pictures here. Okay. So, Sir lost a lot, dons his armor, and sets out from the
Oh my
castle on
God.
his trusty steed. Usually the drawbridge is lowered to a horizontal position so that the end of the bridge rests on the stone ledge. Unfortunately, Lost-a-Lot's squire didn't lower the drawbridge far enough and stopped it at 20 degrees above the horizontal. The knight and his horse stop when their combined center of mass is 1 meter from the end of the bridge. The uniform bridge is 8 meters in length and has a mass of 2,000 kilograms. The lift cable is attached to the bridge 5 meters from the hinge. 5 meters from... Okay. 5 meters from the hinge downward. Okay, so this is 5 here. This distance is 5. And at the castle end and to a point on the castle wall 12 meters above the bridge. Lost-a-Lot's mass combined with his armor and steed is 1,000 kilograms. Determine the tension in the cable, the horizontal and vertical force... The horizontal and the vertical components of the force acting on the bridge at the hinge.
The loser.
Okay, let's write down what we know. So theta equals 20 degrees. Let's highlight everything. That there. So D is 1 meter. D equals 1 meter. And a uniform 8 meters in length. L equals 8 meters. The mass of the bridge is 2,000 kilograms. The distance, I'll call that I don't know. Well, what do I call that? D2? No, that doesn't make sense. I'll call it just whatever, A. So A equals 5. And height equals 12. And the mass of the horse, but combined with everybody, whatever, the mass of horse is 1,000 kilograms.
Wait, I'm confused. Oh, wait. Okay, never mind.
Got it? So there, there. Okay. Determine the tension in the cable. Okay, well, let's start drawing our... let's start with torque, because torque seems like a good idea. So there's our axle, or axis of rotation. So what is all the forces acting on this? So there's a force of tension pulling it up. There is a force from the center of... Well, there's a force of the actual weight of the bridge going down. Yeah, there's a force of the actual weight of the bridge going down. Oh, no, going straight down. And there's also the force of gravity of these guys on it. Any other forces on that axle? I don't think so. Anything causing a torque?
Yeah.
Yeah?
There is.
What is the other?
There's a torque because of the distance. I don't
From-
know, but do you need to calculate it?
From who? Where's the torque coming from?
The oars.
Yeah, that's
And
this
the-
that's this gravity. This gravity of them here. That's this force of gravity from the horse and the guy, and this is the force of gravity of the actual bridge. And this is the tension.
Yeah.
Right? Okay. So yeah, let's figure out how much all this stuff is happening. Okay, so the torque the sum of the torques equals 0. This torque is positive. These two torques are negative. So I'll start with the positive one. So the torque, it's going to be the torque done by the tension minus the torque done by gravity and the torque done by the gravity on the horse equals 0. So the torque done by tension is its distance from the I'll just write the formula 1. So the torque is the distance from the axis, the axle, whatever, times the force times sine theta. Okay, so that's going to be the distance is 5, the force is the force of tension, and it's going to be sine of 90, right? So the torque done by the tension is just going to be 5 times the force done by the torque. Okay, so I'll put that, well, I'll write them all after. So the force, the torque done by just gravity is going to be its distance from the axle, which is going to be half the length. So half the length, the whole length is 8, so it's going to be 4 meters, times the force of gravity on the bridge, right, times sine of the angle between those two things. So what's the angle between these two? If they're tail to tail, so it's going to be 90 plus theta. I think it's going to be 90 plus theta. Right? Because this is this vector, but you don't count this as theta. You count that as theta, right? Because from tail to tail. So it's going to be sine of 90 plus theta, and then the torque done by gravity on the horse. So let's say well, it's fine. Torque done by gravity on the, it's fine.
You can use cos theta. Yeah, 90 plus theta is cos.
Sure, but just to keep it like,
Okay.
yeah, I can. But just to keep it like we're still using the formula. Yeah, that would be that.
Why is it plus, not minus? Like
Because
a
it's
little
Can you
triangle?
spell plus?
I'll draw it a little bigger, right? So there's the bridge. There's the point where the force is acting, right? There's the point where the force. Oh, there's the point where the force is acting. Force of gravity on the bridge, right? So the radial vector, say the hinge is here. The radial vector is like that, right? And so theta is the angle between them, but the angle between them from tail to tail, right? So it's this angle, which is going to be. Sorry, that's not theta. That's the angle we're looking for. So phi, I guess I should call it. And phi is just going to be 90 plus theta.
Okay, that makes sense.
So I actually don't understand the radial thing you just mentioned, and it going past that point.
Well, the cross product is always the angle between the two vectors tail to tail.
Yeah.
Right. This, if I chose this, it wouldn't be tail to tail. It'd be tip to tail. Tip to tail.
Yeah.
Right. So I need tail to tail. So just to do that, I just move this vector a little further forward, and then what's the angle between those two? If I were to just pick up this vector and then move it here, starting here to here, well, then I'd figure out that angle.
Yeah, I think I get it.
Vectors don't depend on the starting position at all.
Yeah.
So yeah, although you usually talk about them like that. So torque done by gravity on the horse is going to be its distance. So its distance is 8 minus 1. It's 8 meters minus 1 meter. So 8 minus. So it's going to be 7 times the force of gravity on the horse times sine of, I think, the same angle. Yep, same angle. Sine of 90 plus theta. Okay, I'll put all these things in. So 5 times the force of tension minus 4 times the force of gravity on the bridge times sine. Okay, I will do cos. Let me just make sure that that's proper. 90 minus, yeah. Sine, yeah. So it's going to be cos theta minus 7 FGH cos theta equals 0, right? And so now we have one of our equations. Okay, all these things I can figure out not too difficultly, right? Not too hard. It's like not too bad. So I would just need, this is just mg, right? Mass of the bridge times g. Mass of the horse times g. So we can figure out all those things. So it's not too bad. We know this, we know this, we know this, we know this. We don't know this. Oh, we can just solve. We know everything.
Wait, sorry. How did everything become cos?
Because sine of 90 plus or minus theta equals cos theta.
Okay.
I have a question. Why is your the torque on gravity like 4 for the bridge?
The distance from the axle. So if the whole bridge is 8, the center of gravity of that bridge is going to be halfway through, so it's going to be 4 meters.
All right, thank you.
I can just solve now, can I? There's no other things needed. I think, let's see if it works. So it's going to be 5 times the force of tension is going to be equal to 4 times the mass of the bridge times g cos theta plus 7 times the mass of the horse and the guy times g cos theta. And just divide the answer by 5. So let's see. 4 times divided by 5. So mass of the, 4 times mass of the bridge is 2,000 times cos of theta was 20 plus 7 times the mass of the horse and the guy, which is 1,000, times 9.81 times cosine of 20. Let me just make sure I put times 9.81 here. I did not. I forgot to put times 9.81 in the first one. Times 9.81 divided by 5. So I got 27,655. So Ft equals 27,655 newtons. Is that the answer? This is number 11.
Yep.
That is?
Yeah, rounds to 27.7.
Yeah.
Yeah.
Good. Well, there you go. So we didn't have to do any other kind of work. It was just some of the torques. That's all it was. Some of the torques. Yeah, there you go. That's pretty good.
Did you have? Did you just substitute the values of MB and MH? And yeah.
I knew that
and
from the
theta?
question, right? Yeah. I just substituted all these values and then divided by 5, and then I got that.
And tension in the.
Well, that's what we're looking for. We were looking for a force of tension, right? So it's.
I'm talking tension GH. That was given.
Tension
Okay.
GH? No, we don't. Force of gravity on GH. That's what we had that. There was no tension GH. Because it's like GH is
Sorry.
gravity on horse. Yeah.
It's the yeah, my bad.
No. Yeah. So we were given the mass of both of them, of the bridge and the guy.
Yeah. Scroll down a bit from please. Oh, okay.
So what was the angle that we used? 90 plus like 20, or is it like
90 sine of 90 plus 20 is the same thing as cos of 20, so we just use that, cos of 20.
Oh, cos of 20. Okay.
Because this again, sine of 90 plus or minus theta is cos theta.
One thing though, you have, it's kind of confusing right here. This is on its own, right? Because like you have equal to 0 TG. It's like there's a line right here, right? Yeah. Okay. Yeah, that makes
that
more
better?
sense.
Okay. Yeah. There you go.
Yeah, because like how did this come to? Yeah, that makes a lot more sense. Yeah. Okay.
Good. So then part B is the horizontal and part C is the vertical components acting on the bridge. Force components acting on the bridge at the hinge. What force is acting?
T for the tension or the torque tension.
For the tension. Well, so it's the distance from the axle, right? So that's 5. It gives us that. It says the lift cable is attached to the bridge 5 meters from the hinge, times the force of tension, which is just the force, which is the force that's acting there, and times the sine of the angle between them. But sine of 90 is 1. So it's just 5 is the distance, the force is the force of tension, and sine of 90 is 1. So technically times 1 here.
Okay, thanks.
No problem. So we need the force acting at the hinge. So what force is acting at the hinge? Well, it's not moving in any direction. So what's the force acting at the hinge? If the hinge wasn't there, what would happen? The bridge would fall.
I think now we're gonna use the net
The
force.
horse would just slide back and just like fall through that because the rope isn't in the middle. It would be like one of those beam balances.
So which way is there force? Okay, so there's a force of gravity there on that? No. Well, it's not.
I think the force
I'm
of
confused.
hinge
What is it asking for?
The
Right.
the horizontal and vertical force components acting on the bridge at the hinge.
Oh.
It's gonna be kind of like a normal force, like that whole bridge is like shoving into the wall, and the wall is gonna push back against it.
Okay. Let me bring the picture. Let me bring the picture down here, and we'll keep going. Let's just try to do some of the forces, and see what happens. So some of the forces in the, if I call that or should I do it along the bridge? No, I don't think I should do it along the bridge. So that's my Y and that's my X. Okay. So some of the forces in the, I'll start with the X direction, is equal to 0. So there's the force, the normal force pushing back this way, right? And there's also the force that's going into it, I guess like that, on that angle. And the X component of that is minus F, I'll call it the applied force, cos theta. Guess so, yeah. And then some of the forces in the Y direction is equal to 0. So there's the force, the applied force going down as well. So it's going to be minus FA sine theta. And what other force is acting on this in the Y direction? Well, there's, we wouldn't say the gravity of that thing. No, there's no, the gravity is acting somewhere else. We don't have the mass of the hinge or something like that.
The normal force again, I think, but in components. Like it's gonna have to balance out whatever is pushing it into the wall. So I guess there'd be like Fnx and an Fny.
Oh, the normal force is going this way. Yeah, the normal force is going back into it like that. isn't it? Oh, no, maybe not. Yeah, no, I think that might be right. So this is Fn, it was x first, so Fn cos theta. And this would be plus Fn sine theta equals 0. Let's see if it works. What do I know? I know cos theta, sine theta. Wait, why are those both cos theta? Oh yeah, okay. Sine theta. I don't know. Yeah, well, it looks like I can solve. So let's see. So, if I have, okay, I'll take the first equation. So it's going to be Fn equals, oh, the cos theta, this is all going to cancel. These things are all going to cancel. So it's just, oh, well, we don't have much here. Fn equals Fa. Fn equals Fa. That's all we got.
Probably torque then, my bad.
Probably what?
Torque would have to help us now.
Torque, yeah. So, but actually, torque wouldn't help because if we're saying the axle, the torque on this is 0. There's anything on the torque.
Oh, we forgot the gravity in the x direction. Isn't gravity in the x direction?
In the y direction?
Oh, sorry, my bad. Yeah, x
actually,
and y direction. No, x and y direction, right?
Y, x, and y.
Because it's at an angle. So
But
gravity is going straight down, so it has x and y components.
But if it's going straight down, it would only have y component.
No, draw.
He didn't do a slanted axis. He did it like a straight axis, like we normally do.
Yeah.
Yeah. So since the board is slanted, if you do gravity, then it
That
has
doesn't
an
mean
angle.
anything.
We're looking at the forces on the hinge. The hinge isn't slanted. The hinge is just on the wall.
So wait, what's Fa cos theta? What's Fa cos theta?
Fa cos. Where did I get this from?
In the x. Yeah, right there. Where's that?
It's the applied force. The x component of the applied force. That dotted red line I just drew.
Only force in the x direction. Like the gravity is also like acting on the hinge.
It is just in the y direction though. Just straight down. The negative.
I think
the
we
negative.
should try it with like the coordinate. The what is it called? The axes tilted.
Someone posted something in discussion.
Let's see. How do I get there?
If you make the axes straight, then tension has two components. Tension is going to have to be included.
But tension isn't acting on here. Isn't acting on this hinge right there.
I kind of got an idea that maybe it would help because net torque is not going to help us at that point, but it'll be 0 about any point. So if we choose another point, then we can include that part in our equation.
Yeah.
I don't know.
I have a better strategy. How about all we can do is just look at the forces that are acting away from the hinge, and take the opposite direction because it has to cancel out because it's in equilibrium.
N equals Fa. So like all the forces that are acting like opposite to it is the same as F applied.
Or is it just basically the tension, like really related, just the tension that is countering?
That's what I'm saying. Tension needs to be included in the x and y components, but.
Adam, sorry, I had a suggestion.
Yeah.
So, like, we can imagine what would happen if the hinge wasn't there. So the whole bridge would swing to the right? So
would
the
swing,
hinge
like,
is
down, yeah,
pushing
yeah.
upward, right?
Yeah.
You can consider that.
Mhm.
So we can draw a force for a hinge somewhere between the bridge and the wall.
So the force,
With
the hinge is applying some sort of
triangle.
force like this up.
Yeah, maybe a little tilted, but yeah, it's okay because we don't know the angle. So yeah, because Dr. Tronov solved a question like this. That was his method. Yeah.
I think that might be what we already got on the thing.
Also send an image in the discussion for PCS.
Yeah, let's see.
Can you guys hear me?
Yeah, I hear.
Can somebody stream because we have
I think
100?
someone else is now. Someone else is now. I see.
Damn, we have 100 people.
We got 100
Yeah,
people
so
now.
can somebody else stream?
I think there's 3
I
people
think
now.
Brian's doing it right now. So if
Oh my
you
God.
amongst the other two, just turn on Brian. Thanks, Brian.
Yeah, you got it.
It's like stream another person's stream. That'd be fun.
Well, that's what they're doing. There's 2 people doing that now, right? So, yeah.
It's great.
What's the limit for one stream?
50.
Damn.
50. Oh, it's we're 100.
Actually reached 100.
Well, we're at 94. It says 94 for me, unless there's another.
Close to it.
Close to it. So. Yeah.
It's 94. It says 94, but that doesn't show everybody.
Yeah, I know it doesn't show.
It's 103, right?
It's 103.
We have 94 people.
Wait, how does it not show everyone?
It always shows a random
shows
number.
like your avatars, and then it says plus.
Oh, yeah,
that's true. Yeah,
plus 3,
okay,
so
1, 2,
yeah, it's
3,
103. Yeah.
Yeah. Oh, I see. Yeah, 100. Okay, cool. Well, there you go. So, where were we with this? So, should I, what I was thinking is, what if we say the torque is here, the axis of the torque is here, and measure but I don't know what the forces are acting on this thing here. Let's zoom in. Like, let's maybe draw the picture a bit bigger. There's the hinge here. There's the bridge going up like that. What are the forces acting right here on this thing?
That might help because it would be like the horse and the knight is like countering the or like the wall or whatever. What's that called? The thing in the wall.
The hinge.
The pin.
The hinge.
The hinge.
Yeah,
Yes.
yeah.
The hinge is
Putting
gonna be counting
the
the
torque
horse.
here. Putting the torque here.
Yeah, and then you don't have to worry about tension, I guess.
Yeah, you wouldn't worry about tension. That's why.
I mean, you could put it elsewhere. You could put it under the horse. I guess you wouldn't worry about the horse, but either way, we know those values.
We know that more. Yeah. I mean, actually, I guess we know the tension too. We know that just as well, but a little bit more complicated.
Yeah.
With that.
Yeah. Either way, I think so.
So, but we still need to know what are the forces here. What are the forces? Or I guess we don't actually. Just the opposite of that is what's acting there.
Because that would have would have positive torque like the hinge, and then the horse would have
true.
negative, right? And then that's the only thing that's happening.
Let's try that. So I have torque acting here. So the sum of the torques equals 0.
Where are you getting this question? Where is it?
The textbook. It's number 11 in chapter 12.
Serway?
Serway.
Okay.
So the torque, sum of the torque is 0. So what's the torque? The torque is the torque caused by that. Okay. Well, actually, there's also the torque caused by the weight of the bridge. So maybe I should put the. Oh yeah, hold on. Maybe I should put the torque right in the middle. Put this right in the middle, and then we know everything else. Yeah, I'll do that actually. I'll put the thing right in the middle, because we forgot about the weight of the bridge. So that's like in the center of mass. So there's the center of mass. The weight of the bridge is not causing any torque. So we have the torque done by the guy here, by this force acting like that. The torque done by the tension, and the torque done by this force. I don't know what to call it. I don't even know what to call the
hinge.
The hinge force. But like, where do I even draw the arrow? I don't even know. Like, up, I guess.
Yeah, there's like 2 components. The one up and
arbitrary.
one.
It's arbitrary.
Yeah, I guess technically we don't know until we really solve it.
Okay,
so
I'll draw it like that, and then yeah, we'll see. Okay, so the torque by, so it's gonna be so I'll call this the horse. I'll call this the tension, and I'll call this the hinge with an I. So the torque done by the horse, is that going to be positive or negative? It's going to be negative. Okay. Plus the torque done by the tension, plus the torque done by the hinge equals 0. So we're pretty much solving for this. Well, I can break it up and then we'll solve for that. So torque done by the horse is going to be its distance from the axle, right? So its distance from the axle is, if that's at 4, right, halfway up. The whole thing's 8, halfway up. And this is 1 meter from the end. It's going to be 3, distance of 3 there. So -3 times the force, which is just the force of gravity, which is just mg, times sine of the angle between these two things, which we said is going to be 90 plus theta. Sine of 90 plus theta. Okay, which again is cos theta, but that's okay. So this angle is 90 plus theta. Okay. Plus, for the tension, how far away is the tension from it? So the tension is 5 meters up, so it's 1 meter. It's a 1 meter difference because this is 4. We said the tension was 5 meters up, so there's a difference of 1 there. So it's just 1 times the force of tension. I'll just write it as the force of tension. Times sine of the angle between them. That's just 90. So it's just the force of tension. So sine of 90 is 1. Right. So.
Yeah. Isn't the hinge trying to bring it clockwise though?
Yeah, it is.
So shouldn't it be negative?
I didn't do the hinge yet. This is the hinge over here. That's the next one I'm doing. This was the.
Yeah,
This was the.
Okay. Yeah. Okay.
Oh, actually, hold on. Yeah, this one. Sorry. Wait. This. Oh
yeah,
yeah.
the third one.
This should be negative. That should be negative. Yeah. Sorry.
Yeah,
that should be negative. Sorry, I didn't understand. That's right. So then I'm subtracting the torque done by this. So it's going to be the distance from the axis, which is 4, times the force. That's what we're looking for. This is the thing we're trying to solve for. FA, right? Well, I'll call it FA. Times the sine of the angle between those two things. So the radial vector, so that's again going to be 90 plus theta. So sine of 90 plus theta. Okay, and that equals 0. What do I know? Theta, force of tension, theta, mg. We know everything. We just need to solve for FA. So I think I can just do this. I think I can just say, okay, force of tension minus 3 mg sine of 90 plus theta, right, equals 4 applied force sine of 90 plus theta. I'm going to use the rule here that's sine of 90 plus or minus theta equals cos theta. So
Plus or minus.
Plus or minus. Yeah, so well here is plus. So ft minus 3 mg cos theta over 4 cos theta equals fa. These can cancel. So the applied force is equal to ft minus 3 mg over 4. Let's see if that works.
The ft, how do you cancel cos theta if you...
Oh, you're right. Yeah, I can't do that.
Okay.
You're right. Yeah, you're right. I can't do that. I didn't see that. I didn't pay attention close enough to that. That's just there's still a cos theta there. Yeah. So that line's useless. So
we're gonna get the absolute or the magnitude for the force anyway, though. We need x and y.
That's true. So we gotta choose a direction. Well, no. I can still just say. Okay, let's get the magnitude and then I'll think about that in a second. Okay, so the force of tension is 27,655. 27,655 minus 3 times the mass of the horse, which was 1,000, times 9.81 times cos of 20 degrees, all over 4 times cos of 20 degrees. So that is the magnitude of FA, which is the magnitude of FA equals 27655 minus 3,000 times, I'll put more brackets so we don't get messed up, 9.81 times cosine of 20. Okay. Then cosine of 20, then I'm going to do 4 times cosine of 20 on the bottom, and I get negative 0. Well, how did I get an absolute value that's negative? Negative 0.04 newtons.
Means that is going to the opposite side.
Okay. Yeah. Sure.
We were thinking.
Makes sense.
Sure. Okay, so then if I put this like that, then that would be positive.
Now you put sine 20 cos 20, you find the.
Well, but look, it's going straight down, isn't it? If it's going straight down, then it's just the x component. Well, let's say it's going on some angle. Okay, hold on.
It's going some angle because there are two component because it's an angle.
Where
the
do
torque
I...
does it take the force and that's it.
So put it there.
I'm looking in the answers right now, and it's giving the components for B and C, right? But like, that squared plus that squared square root answer is giving 12,239.
Yeah, no. That's a very small amount of newtons too. That's like tiny. It's nothing.
Impossible.
So, what happened?
You know, our force, tension, and the other stuff are like exactly the same. What?
The one thing I did think, if we put the axis about the tension, then we wouldn't include like a number we got from the previous part, but we know that it's right anyways. I
We
was just
know it's
thinking like
right,
if it was like on a test or something, if we didn't know, like you don't know if it's right or not, then it's good to avoid.
Yeah, for sure. I agree. That would be good to put there. So
Can you clear up that last? Yeah.
So looking at a
Wait, did you-
solution here. Someone said, yeah.
It's not negative. How did we get FT minus?
Minus here because this was minus. The torque done by the horse is negative. Because it's pulling it in this direction. Oh, okay, so someone's saying, so the y component of the hinge counteracts all the vertical forces we know. X component of the hinge counteracts all the horizontal forces we know. So just do the sum of them, and that's the component. Yeah, I guess. Like, well, what isn't that? Well, okay. So just the sum of all the forces of everything in the y direction. Oops, a little too big. Would that be right? So I have some force acting in some direction here. It counteracts. We didn't use the height of this wall at all, too. At all. So...
Did you even need it?
Well, I don't think so. But I'm not sure.
Would be a position vector. Maybe when we're doing a torque or something.
Okay.
That's what I was thinking, but I'm not really sure because the only thing that's attached is the rope or the hinge, maybe. I don't know.
So someone posted here this solution here. I'll put it on here. Someone posted this. Let's take a look. Come on. There you go. So pretty short. So the torque done at the hinge, so the torque at the hinge is equal to T times the whole length minus X. X is what? That. So the torque times that's probably the force of tension. That's the distance. Sine of theta. Okay, that's what I did pretty much. L minus D. D is the distance to the thing. That's the torque done by the thing. Oh, minus mg here. Never mind. Isn't that what I did? This T. Negative?
That is right. I think it's the second part. It's the fx and fy. I think it's what the other person said. Is just all the forces like in the whole system, treating them, even though it's not at that specific point. Like you're just treating them
Oh yeah.
the way they are. Like fx is just the tension in the x direction, and then fy is the gravities, like masses plus the tensions.
But the answer in the textbook says the horizontal is 11.5.
So not this answer.
But I've seen that, like, I see that answer as well.
Yeah, I got that answer too, like a bunch of times. So I don't know if the textbook's wrong or not.
Where are we? Chapter 12, number 19.
Number 11.
Number 11.
That's what I'm getting right. Oh yeah, 11.5 and 4.9. Yeah. Well, okay. So, but other people are getting different answers. So how do you find this? TSM.
Just torque. It's sine theta.
You can just generalize
Sine
the hinge
theta.
force.
Yeah.
You can just generalize the hinge force as to y and x. Like the way they did it. And then you have the components of fy, fx, and then tx, ty. And you can equate them.
Oh, okay. So it's just these forces. So you just say, okay. So you just say this force, the x component. Oh, the other ones don't have x components. Okay. So the x component of this force, the x component of that force is just going to be the fax facts is going to be just the x component of that, because it's going to counteract that. Yeah, okay, the magnitude of that is just going to be that. So the magnitude of that is going to be the force of tension times the sine of theta. Okay, sure. And the FAY is going to be the y component. So there's a y component here, yeah, which is going to be negative. Wait, the y component here will be positive. Unless they define their axes differently? No.
No, they just brought it over because it's fy minus mg minus mg. Yeah, and then plus thing, and then you bring it all over to the other side, and they all become positive, positive, negative.
Oh, okay, I see.
Yeah, they just skipped the first step. That's why.
So the sum of the force. Oh yeah, okay. So the sum of the forces in the y direction is going to be positive at force of tension cos theta. Then it's just going to be the minus the force of gravity on the negative to that. Okay. The force of gravity on the bridge and minus the force of gravity on the horse, and that equals yeah, it's kind of confusing how I'm saying it, but I'm trying to figure out what the sum of the forces is, and then the negative of that is what the hinge force is going to be, because it's counteracting all of it. Right? So the negative of that, so I'll say the Fy hinge equals the negative of that, which is the negative of this, so it's going to be Fg on the hinge plus Fg on the bridge minus the force of tension cos theta. Yeah. So Fyh, the force on the hinge in the y direction is this. So there's our two expressions. I guess I could just write it here actually. The force on the hinge in the y direction is going to be that. So there's our two expressions. We can just plug everything in. So the force of tension was 27,655 times sine 20. So 27,655 times sine 20 is 9,459. Is that the answer? Well, it's not the answer, but it's the same answer that they got on this. And did other people get that same answer?
Yeah, I got the same answer as well.
Yeah, I see. Okay, well, I think we'll go with that. So then this is mg, so mass of the horse times g plus mass of the bridge times g minus ft cos theta. So that's mass of the horse is 1,000 times 9.81 plus the mass of the bridge is 2,000 times 9.81 minus force of tension is 27,655 times the cosine of 20. So I got 3 1,442.8 newtons. So that is construction here again, so you probably hear construction noises. But yeah. So,
I'm confused. I don't understand how. So why is the force of the horse in the y direction equal to negative force in like the negative sum of
yeah.
Fy?
Well, because if this force didn't exist, this would start moving. Everything would start moving, right? Based on these forces, it would start. This would start like, this would still pull it up, but it would start pushing it like this. Like imagine how it would move, right? I feel like it would move down and kind of move to the right, right? And so what that means is that this whole thing, this is what's keeping it in equilibrium, right? This piece right here, the hinge force. And so the hinge force is just equal and opposite to all the forces of the rest of the system. All the forces of the rest. So it's just the sum of the forces in the y direction for the rest of the system. The negative of that is going to be our force in the hinge force in the y direction. And then, it should be the negative of this too. Sum of all the forces in the... Yeah, it should be the force of the... I call it the hinge force in the x direction. Yeah, well, it should be the negative of that, shouldn't it?
It is the opposite. Because if you do Fax minus Ft sine theta equals 0.
Oh, okay.
Yeah.
Yeah, that's true. That's true. So if I say F hinge x equals negative sum of the forces in the x direction. Sum of the forces in the x direction is just negative force of tension cos theta, right? So then the force, the hinge force in the x direction is just positive force of tension cos theta. And yeah. So, big question, weird question. Long one.
Is that isostatic structures? Always.
Yeah, they're gonna be
Can we
tricky.
recap?
So wait, yeah, can we recap? And are we assuming that the textbook's answers are wrong then?
Oh, I guess so. We are, because I don't know. Yeah, I guess so.
Yeah,
I found multiple things on the internet that has the exact same answers that what this person wrote. So I think they're wrong.
The textbook's wrong.
Yeah, the textbook was wrong.
Yeah.
Because I found at least 2 sources that say that was the right answer.
Yeah. Okay. So that's good for me. I'm good with that. And yeah, I'll recap. So part A was started up here. Part A is just find the tension in the cable. So I did that using torques, right? So the torque is 0. I said the torque starting at that, it doesn't matter where you choose where the torque goes, but started there. The forces acting on it is the force of the gravity on the bridge, the force of gravity on the horse and the guy, and then the force of tension. So I found the torques, the 3 torques relating to those forces. And then I noticed that the sum of the torques is equal to 0, right? So, and I have everything in that equation except the force of tension. So I just solved for the force of tension. Then for part B, part B we did a lot and then ended up just doing this, is that, the sum of the force that this is acting, that the hinge is doing, right? The x component of that will counteract all the other x components. And the y component of that will counteract all the y components, right? So what we just did is we just did exactly that. The force of the hinge, the x component of the hinge force, is negative the sum of the forces in the x direction, which is the sum of the forces in the x direction is negative ft cos theta. So the negative of that is just ft cos theta. Just plug everything in, we know all the information there, so I got that number. And similar in the y direction. The hinge force in the y direction is the negative of the sum of the forces. So there's the sum of the forces, right? The tension in the tension force in the y direction, and then the 2 gravities. The negative of that is that. Plugged everything in, got that.
Yo, just for the first part, one of them was just 5 f of t, right? Or tension, and then we just solve the tension.
Exactly. Well, yeah,
Yeah.
we just one of them was just 5 because the distance is 5, and then
Yeah.
force of tension is the tension, and it was sine of 90, which is 1.
Yeah. Okay. And then can you scroll down?
Mhm.
Well, keep going. Like we can skip all this since we didn't really use it.
Oh yeah, you're right. Yeah, this part.
Yeah, this is A and B, right? Because it's horizontal and vertical, right?
B and C. This is B and C.
B and C. Yeah. And FT cost was like, what was that? There was the
FT
90
cost.
plus the thing.
Yeah, the reason it turned. Yeah, sorry.
Yeah, can you show me?
How did it turn into
for
cos theta?
Yeah.
Well, this rule here, sine.
I mean, on the beam, on the
Here?
what angle are we using?
We're using
On the picture?
for on the picture for the tension, we're using this angle in here, theta, which is the same as theta. It's the same.
Hmm.
So force of tension times cos theta would get you this vertical component.
Okay.
Because cos theta is adjacent over hypotenuse. So cos theta is the adjacent is going to be the y component that we want. The adjacent here is the y component, right? And the hypotenuse is ft. So we can rearrange this and say ft cos theta equals the y component.
Yeah, okay. Yeah, okay.
Okay. So yeah, there you go. Okay. Well, I think I'm going to take a little bit of a break before the next question, but we can still answer some questions, like if people want to clear this question up, and then I'll take the break after. So, yeah.
Can you just complete the triangle of that you used to kind of get the F cost and the...
This one?
Yeah. Can you complete it? It's the rope is the hypotenuse, then...
Yeah. This is ft, this is fty, and this is ftx. That's theta, right? So if I'm looking for this one, I do this, right? So it's cos theta is adjacent over hypotenuse, so it's fty over ft. And I'm looking for fty. That's the point, right? I want the y component, so I multiply that to the other side.
Cool.
And then similarly for sine, if I wanted to find the x component, I just use sine, right? So it's going to be sine theta is opposite over hypotenuse, right? So opposite is fty, right? So sine theta is ftx,
Yeah.
over ft, right? So ft sine theta equals ftx. Yeah.
All right, thanks.
Let him take a break.
Yes, I will take a break after this question. So yeah, probably I'll take like a 20-minute break because I'm gonna make myself some lunch, and then yeah. So is that good with everybody? Take a 20-minute break.
It's a good idea. We should. I feel like it'd be bad to be like our brains fried before the actual exam too.
Yes, for sure. Yeah. So yeah, I'll take the break now. So I'll say 20 minutes from now. Everybody's gonna see a beautiful transition. Ready? There.
Damn, we ending it on an even number too. Almost 12 o'clock.
That's true. Almost, right?
Let's just wait.
That is
30 seconds, let's see what
important.
it is.
Transition are important.
Yes, very important. So
after test, okay.
Yes. 12:20. There we go. So I'll be back then. So everybody take a break. Everybody take 20 minutes. I'm gonna make myself some food, and everybody should also probably eat if you haven't already much yet today. So yeah. Okay. So I'll talk to you guys in 20 minutes.
See ya.
Bro, why?
Allow him, bro. Let's watch him get crushed.
Hello, guys. Do you have a formula sheet for physics?
Yeah, there's 2 posts.
Yeah,
I
they're
think they're pinned.
Where is it?
Discussions probably.
Discussion.
Yeah. There's one from Vikram called Physics Compressed, and then
Who's
if you
asking?
scroll down a little bit, Casper's formula sheet
Yeah.
is there too.
I just resent it.
I like the I like Vikram's more. It's got little notes on them.
I'm gonna tell Jasper that.
So, physics compress. Oh, thank you,
Which
guys.
one? The one on the
See,
summary.
the Physics Compressed is bigger because it's better.
You mean the one with the pictures and the actual?
Yeah, with notes and shit like that.
Oh my gosh, it's beautiful. I don't know how people. Kudos to you guys who actually can dedicate yourselves to that. I am so proud of you. So there's also a next just random photo with like theorem of parallel axis and everything
The
else.
problem is I'm not I'm writing very bad, so I'm very disorganized. So
Oh,
my
really?
formula sheet is always bad.
And then there's that as well that I just sent. And I think you only need like the moment of inertia, rotation, and parallel axis theorem. Everything else, well, most of it. I don't think we'll get. Have you anybody else like seen any perpendicular axis thing? Because I don't even know what that is.
I'm sorry. Where was this?
Yo, Musa, I love your slideshow.
Thank you. Where was the
Key, where are you at?
formula sheet again?
In discussion.
Discussions.
In discussion right now, we just resent all of them.
All right, found it. Thank you.
That shit's way too laggy, bro.
Just so I can destroy you.
How many frames were you getting?
Not a lot. It's fine on my screen, but the live is pretty shit.
Mac things.
Vishal, I'm 1v1ing Key. You're not even getting on. Shut up. 1v1 right now, Vishal. Or stop talking.
Stop 1v1ing in Minecraft, holy fuck.
Yo, all I need
Just
to
that
say,
easy.
all I need to say is Mustard's trash. Whatever he
Okay, if
says,
any of you have guts, come on the server and 1v1 me fisticuffs.
Key, where are you?
You have some
Wait,
next
what's
level
that?
bravery for saying that.
Musta,
What in the
Musta.
world?
Yo,
What?
you're trash. You're
Yeah,
trash
I mean,
at
get
Minecraft.
on the Minecraft server.
You're trash at Minecraft.
Yeah, get on the
alright?
Minecraft
Just
server.
stop.
1v1 me
Vishal, you have
fisticuffs only.
100 deaths.
Stop.
Stop talking.
Where's Priyaji in chat, bro?
Not even Vishal.
Yo, this guy. Yo, look, Musta. Whatever you do, I don't care what you do. I don't care how much like your
Muska.
kill to death ratio is. You're still trash.
Then
Just
1v1
regardless.
prove it.
Yo, listen,
Yo,
you
I
guys
don't
are
need
talking
Yo,
about
1v1 me,
Minecraft, just
kid.
leave it.
1v1 kid. You're trash.
Yo, I don't need to 1v1 you to prove it. You're just trash.
1v1 scrub.
Yo, Key
1v1
will
me,
do my work.
MC
Key
plays
will do my
PvP
work.
man,
Alright,
bro.
this is
Wait, wait.
turning
1v1 me,
into a god
PvP
lobby.
man, kid. This is
This is turning into a god lobby real fast.
If
Key, what's
PvP,
your
then I'll
fucking
consider.
username?
This is a Fortnite lobby, not
Hold on,
even
put it in chat. Put it in chat. Hold on. Wait. It's in fucking
Minecraft. This isn't COD.
Oh yeah.
1v1 me.
COD lobby's way
We're
worse
same
than
kind
us.
of competitive
look at
energy
homework
for
talk, bro.
Minecraft.
At least it's entertaining.
You're a noob. Wait,
Oh
who
my
we talking shit
god.
about?
Dude,
Guys,
this
Who we
is
talking
not
shit about?
2012. What are
Who we
these
talking shit about?
these insults?
Who we talking shit about?
Vishal.
I bet you can't beat Minecraft in 30 seconds. Wow, you suck. Like,
Wow. I wish I could, bro. I'm not that
yeah.
good.
Fucking, what the hell, man?
I never
Okay,
played
fine.
Minecraft.
You should
Did I
play
miss
Oh,
Musta's
Minecraft.
dude, same
streaming?
here. Same here.
I
Minecraft's
never
literally the
been
best
in
game
Uva
ever.
Java.
I sweat Bed Wars, personally.
Musta, to see your stream.
Pardon?
Let us watch Minecraft. We want to watch Minecraft.
Alright, I got you, bro.
I want to watch a slide.
As much as funny enough, I even though I like 1.8 PvP better, I did better on 1.9 Bed Wars. I did better on the like with the 1.9 plus Bed
Yo,
Wars.
y'all are talking about game fucking versions now? Holy shit. Yo, relax.
The thing is, after like 1.11,
Worry about physics. Oh my god.
after 1.11, it just gets so glitchy. You just get into glitched every other block, so it's not fun playing Bed Wars.
1.11, guys. This is you are pro.
No, it's just like it's known in the
chill,
PvP
you know.
community. It's just known because it's like horrible. Is it? Wait, is someone street? My brain only has GPU RAM, so I gotta be careful. Minecraft nerds have arrived. Wait,
Only
wait,
real
this is-
legends. Only real legends play Microsoft Paint.
Wait, is this the same Bischoff from the other server?
What the fuck?
That's Musa Job. That's the guy that puts the quotes that 5 people read.
Shut up.
Hey, I know
All
at
due
least
respect,
6.
I
I know
read them.
at least
Don't
6.
worry.
I know at least 6.
That's crazy. Yo,
That read 'em.
Emmanuel,
Musa
thanks for
Job
giving me
doesn't count
prims.
as one. You have to.
Musta,
Yeah,
I
no
read them.
worries.
I
Musta
believe in
doesn't
you.
count as one.
Yo, Josh, I'm disappointed you didn't put your ice cream flavor on the announcement.
That was too fast, bro. Come on.
Dude, you
No,
know what?
is it
Next
14 plus bonus
semester,
or is
next
it?
semester, I'll let you know the
Guys,
flavor.
guys.
Wait, what? I can't hear.
Serious question. Is it 14 plus bonus or is it a 13 plus bonus?
13 plus bonus. 13 plus bonus.
Oh,
13 plus bonus.
Oh, okay. I'll just.
I think 13. Yeah. No.
Yo, do you read my announcements? Come on, bro.
Wait, what are you guys talking about?
Wait. Which announcement?
Which announcement? The one in announcements?
Oh, okay.
Wait,
My bad.
Yeah, he said he's gonna get ice cream. He never told us what flavor.
Yeah, exactly. What ice
Yeah,
cream
what flavor, bro? What flavor? What you
Okay,
say?
it's extreme chocolate. Extreme chocolate.
The hell's extreme chocolate?
Bro, it's extreme.
Normal chocolate not
What is that? Like 3
That's all you
chocolate?
need to know.
Hey guys, today we're
Extreme. It's
playing
just extreme.
Minecraft Let's Play.
Oh, Manuel. Oh, that's cool.
Yo, my
I
bad.
wanna watch.
No, play Bed Wars.
Normal
Hey, what
games
are you
in a
doing?
while.
What crack are you on? Play Bed Wars.
Watching unless you have like 5 frames.
I have more than 5 frames, I'm gonna show you. Oh, it's broken.
People.
Is that an AMD processor?
No
Oh, yeah.
way! You are on half a hard, bro.
Oh, I gotta change my controls.
Wait, why aren't
This
you
is
streaming
disgusting.
this, bro? I thought you wanted to like stream.
Wait, Manuel, what the hell are you? Okay, I was about
Why
to
do
say,
you
what are
have
you
shift
streaming?
as your mouse button?
What? No, this is my. It's my side button.
Yeah, exactly. Why?
Cause I'm fucking cool, all right.
It's
Well,
always
why
the shift
not? You
button.
can easily shift.
Oh, well, I
Oh
guess
my
every
god,
other
auto
game
jump
shift
is
to
on.
sprint.
Yay.
But I guess every
Okay,
other game
no,
you
if
shift
you
to sprint.
have auto jump on, just quit.
How do you have so much range?
Because he has a gaming
It's called
PC.
having a
Are you calling me a
computer.
hacker, bro? That's
Bro, I don't even have a computer.
It's called. Where's the FPS?
75?
Oh, 75. Insane FPS, bro.
No,
What's
I
locked
have
at
V6
While you're
on.
streaming?
I'm pretty sure
Lock.
he has
75 while you're streaming? Holy shit, you have a good computer.
It's not that much. Oh, it's not locked.
And fancy graphics? What is the
Whoa.
Guys,
lock
oh
that
my
in
god,
there.
guys, fancy graphics in Fortnite. I mean, in Minecraft.
Minecraft.
Can you say?
Not even kidding. Without Optifine, even on fast graphics and like the lowest settings possible, I could barely get 10 FPS standing still. My computer is
What
such
are you running, dude? I can get more on my laptop.
Exactly. I have integrated.
No,
got
I'm not
more on my
joking.
phone.
My computer has. My
I dropped my
processor's
bow.
Intel Core 2 Duo.
Say what?
I don't know.
It's literally 2 processors with a 1.8 gigahertz each. It's so bad.
Oh my goodness.
You
need it.
Oh, guys, we found coal. This is so great.
So
Oh, what? You can get coal with a
So,
wooden
with
pickaxe? Fuck.
So you have
Wait, you didn't know that?
Intel
I thought I was trolling.
i5 or
I
i3?
have a
He has a
Ryzen 5
Ryzen.
1600X.
I don't even have an
That's pretty
Intel
good.
i-Core. I have
1600?
an Intel Core 2 Duo.
1600X
Oh, you have a
you have?
1060, so that's probably why.
No,
You guys have
Minecraft
CPUs?
is CPU intensive.
You guys have
But
CPUs? What?
Yo, if
everyone,
Manuel had a 30 series, I would go to his house and rob him.
if I had a what?
If you had a 30 series graphics card.
Yeah, exactly.
All the boys would just go to your
Yo,
house.
guys, better yo. After the exam, want to run a better for me? I'll literally destroy all you. I am better sweat.
Alright, bet.
Okay, well, I mean,
I am very
Daniel,
out
are
of
you on
practice.
the
but
FYE
I main
server?
Bed Wars.
I was trying to
No,
on
I'm
this
just
afternoon.
playing. I'm trying to fuck with people, but nobody's noticed anything yet.
What are you trying to fuck with us with?
We're
Why
just
are you
gonna make
mining
a house
dirt?
real quick.
Why are you mining dirt? Why is this mining
Are you gonna
dirt?
speedrun
let him mine
Minecraft?
dirt, bro. Whoa.
Yo, he's speedrunning Minecraft, bro. That's why.
I'm speedrunning, guys.
Why are you
Speaking of
talking
which,
sideways, bro?
anyone up for Minecraft Manhunt?
Yo, facts, bro.
What in the world?
Add some mods, add some vein miner, and we should be good.
Where's
Oh,
he
why don't
was
you put
basically off.
brightness to bright? Why is it on moody?
I feel bad for the people who are here to
'Cause I'm
listen to
moody.
Adam. Now they're listening to us.
Yo, where the
Sorry
fuck
about
is
that.
the?
Oh, it's
Oh,
only for the
here.
next 8 minutes. After
Okay,
that,
no.
everyone's
Oh
back.
no!
Okay, now we're getting real FPS. Where's the FPS counter?
180.
156. Top left.
Oh,
Right under
170.
Minecraft.
There you go.
Yo, no,
Okay.
somebody took my spot on Adam's stream. Now I can't watch it. God damn it.
Watch
But there's
the
like
other one.
3 other streams. It's not that
Yo,
many.
guys,
it
we
was
need
me.
to like move
It
into a
was me.
different
So
voice
sucks
chat
to
because
be-
it like reverberates everyone's thing.
Oh shit, you need armor. Hold on, I'm gonna get stuff.
Someone make can one of the admins make a separate voice chat and stream it there instead?
But then they can't talk to Adam here.
Yeah, but then
That's why we have
just
it like this.
join the freaking call and go back because then you have to hear 2 of yourself
Oh, guys,
and 2 of
I'm
everyone
gonna
else.
speed run.
No, just deafen yourself. Deafen yourself when you're watching the other stream. Then you can't hear the
No,
echo.
No.
just mute. You can mute the video of the other
Oh,
person.
Yeah,
only
but
the
then you're not
voice.
gonna hear Adam. Then you're not gonna hear Adam.
That's what I
No,
do.
you
Oh
can hear
no,
Adam.
guys! I
Because they're
accidentally
Adam's
deleted my
stream.
pickaxe. Let me just
They'll be able
repay
to hear him because
myself.
they're in the same voice chat.
So
They
you have
just
netherite right
Oh,
there.
no,
You
did
have-
you-
Yeah,
It's
let me
really
just
good
repay
netherite. Why are you
myself.
letting? Okay, there you go.
Yeah. Oh.
You need to mute the
Actually-
Oh
video.
no!
Not
I deleted my stone pickaxe, guys.
That's stone right there. He's giving
We
himself
gotta pay
back stone
back.
armor. It's
Yeah,
okay.
he's just getting it. He's just getting stone. He's just getting stone. You see
That
stone
makes
box?
sense. Can you do an anviling experiment here to
Oh,
see
oops.
exactly how many enchants you could anvilier?
No.
Anvilier?
Nerd.
Can you do a science
Yes,
physics
anvilier.
experiment? Can you
Guys,
calculate
we got the stone shit.
how high you can drop an anvil without it breaking? Can we do some?
Yeah, but you have
physics
to
right
you
now?
have to be standing underneath the anvil.
I love how this is right before the physics exam.
Okay, but we need
Hey,
to. This
yeah,
is physics. This is physics. Let's see how much.
We're doing
This
physics.
is literally physics. This is literally physics right here.
Yeah, we're doing
Whoa.
physics.
Minecraft physics is also physics.
Okay, how do you
Yeah,
know what he's gonna build?
physics. Yeah, physics.
Please don't, Manuel.
Are you
We need
gonna
the
make an end
physics
portal or something?
experiment.
It's physics, guys.
I want to figure out how old he is. It depends on what he draws.
What do you think he's making, Bo?
This card is annoying.
I don't want to
What
be
is that?
judgmental,
Is
so
that
I'll
the
just
red
wait.
cross, bro?
I'm thinking.
Can you make a picture of Adam as a tribute for him?
Oh yeah. What do you think I am?
Well, I mean, you had brown wool. He's not really brown.
He has brown hair.
Basically, everyone else is. He isn't.
That's true.
So guys, if you don't want
Sure,
double
just go
voice,
learn
you need
pixel
to
art for like 3 months and come
you need
back.
to mute the video of the person that you are choosing,
Yeah.
so you listen only to
Yeah,
one voice.
you can mute the stream.
Yeah.
Oh, also,
Put
what's
Adam is cool.
what's
Adam
chapter
is
4
cool.
and 5? What's chapter 4 and 5? That's like pretty late to ask.
It's some Hiblis. So you just don't worry about it.
It's motion under uniform acceleration and circular motion.
Okay. Right.
Chapter, you don't know. You can know resolve the next one.
Huh?
Yo, people.
Oh, that's fucking ass. Oh,
Wait,
that's
does anyone have MVP plus on High Pickle?
High Pickle?
Yeah, High Pickle.
Yeah.
High Pickle.
Wait, why?
I don't know, man.
Because then we won't be able to run a private game.
Oh, you mean
Unless we
MVP plus? You need.
I have a Minecraft server.
I don't think you need plus. I'm pretty sure you just need
Oh God, that is ass.
Yo, just press pick plus.
Okay. Science experiment, right here. Physics. This is literally physics. Someone get the MD. How much does an anvil weigh? And how much is
mama.
Okay, wait. Hey Google. What's the
we're
average
gonna make
weight of an
this.
anvil?
No. You have to find the weight of
Yo,
a.
So
don't
75
worry
to
about it,
500 pounds.
sweetheart.
So it's 75 to 500 pounds,
Oh.
something around there.
Oh no, you'd have to get the actual average weight of the iron used to make it. That's 3 iron
Yeah,
blocks.
but then we don't know
That's
the
9
density
iron each. How much is the weight of an
Yo,
iron
guys,
ingot?
guys,
Well,
guys,
five
guys,
by-
guys, guys, it's Minecraft. Relax.
But we're
Yo, that's study
we're
for
doing the
physics.
calculations.
Bro,
But we're doing the calculations required.
imagine we had a
Bob, you
science.
are becoming more nerd each time.
But if we don't do the calculations, we're not good.
What are you doing, homie?
Imagine we had a physics teacher who taught us physics through Minecraft. That'd be so good.
That'd be actually great. I would
Horowitz
learn a
would do
lot.
that. Horowitz would do that.
I would worship them. I would
Horowitz would
honestly
do
just
that.
put a
Yo, Horowitz could have been a
put
physics
somehow
teacher,
just
bro,
figure out a way
with
to
the
worship
Minecraft
them.
knowledge he has.
Bro, this one made
Adam?
mod tutorials and shit for this one mod. I'm like, bro, what are you doing?
Who did?
Horowitz.
Today I'm gonna teach you how to kill yourself.
What is this man doing?
He's gonna put the anvil connected to redstone and he starts on the plastic plate underneath. But don't you
Okay.
need repeaters? This is too long.
No, it's not. It's right above 15.
It shouldn't be. I think they're what 16.
All right,
16
boys.
long. I think.
15. It's 15.
Nerding.
And I want to have a
too much.
repeater somewhere. Yeah, that's probably too long now.
Give it a shot.
It's not gonna go all the way up.
Okay, don't worry about it, sweetheart.
Don't call me sweetheart again right now.
Do it. I dare you. Do it.
That was very suspect.
I double dog dare you. Double
That's
dog
not
dare
a
you.
bad thing.
One back. Move it one back.
Yeah, just
Yeah.
simple. Yeah, just gonna have some next level chemical reaction, bro. Let's chill.
How was chemistry, guys?
It was okay.
Oh, he's doing the
That's pretty good. It wasn't that hard. Why would you put a redstone torch there if you already have a thing to?
Bro, I miss those Minecraft days, bro. Those days were so goated.
Oh, be quiet. He watched Mumbo Jumbo. He knows what he's doing.
Oh no, I
Now
don't.
I'm worried.
I haven't played Minecraft for years now. This shit's so lost.
You gotta hurry up. I'm coming back in like 2 minutes.
Oh shit.
Clever.
How are you gonna power a redstone torch, kid?
Wait, no. There's a different way to do
That's
it. I
fine.
forgot how to do it. Oh no, it's
Block. It's a
horrible
block
admin.
thing. You have to touch the torch with the block.
This guy's a horrible admin.
Yo, I don't fucking Minecraft.
You have to
okay?
take the torch behind the block.
Okay, just
This
drop
one?
the anvil on your face. You can just do it manually.
Yeah, but that's fucking dumb.
1, 2.
There
okay,
you go.
Two, approximately.
That was really stupid.
Okay, now we just calculate the mg. I don't know how much mg is needed.
So it's about 500 pounds, and then we
Fuck.
also.
Okay, fuck
So
this. I'm making
500
a
times
switch.
9.2. So 500 times
too
2.2.
complicated.
That's not how you do it. Leave it.
Yeah, that's the conversion from.
Lever.
Oh, sorry, the other way around. So
No,
500 divided by 2.2.
Minecraft fam, relax. It's not that
And then we
serious.
have so it's 227 kg, right? And then
No, but what about the torque? You're forgetting about torque.
there's no fucking torque.
From the
Nothing's
piston,
happening.
from the piston, bro.
the-
From the piston.
There's no torque from the piston,
What?
kid.
Bro, what is this? M1 plus M2 plus M3?
Oh, did you set the piston as the pivot so you just ignore the
Yes,
piston?
yes.
Yo, what are you
okay,
saying? What are you
okay.
saying? I'm just
We're
trying to do a shitty joke. Relax.
We're saying you're gonna fail the test if you don't know what we're saying.
This is
Yeah,
me after the
exactly.
Bro,
test.
I just want to get two questions right.
So
Oh, what the fuck?
You and I. You had the armor on.
Yeah, the right, dude.
Oh,
You gotta
right.
go higher. You
Oh,
gotta
yo,
go
my
you-
head took
oh,
it deep.
Holy shit! What happened
That
to the
was a lot of
durability
damage.
of the helmet?
Yo,
That was a
I
lot of
took
damage.
5
What the
anvils to the head? Question mark.
Okay, so that times 9.8.
Now, how do you get them back up?
Are
9.81.
Okay, fine. We'll do 9.81.
No, it's basically 10. Just say 10.
So it's
Yo,
it's
yo.
2,227 newtons of.
Does this guy
that's
actually have a calculator, bro?
Bro, are you guys for
Yeah.
real, bro? Oh my god, you guys are
I'm
crazy.
not for fakesies.
He was
I don't do
studying for
fakesies.
physics. I don't know what's wrong here.
Minecraft world.
Calculate your acceleration values.
Set
I
the time
forgot.
to day manual.
Oh, your
Probably can.
acceleration when the anvil hits
Probably
your head?
can.
You probably can, actually. You think about it?
You're in
You
creative, by the way.
could because Minecraft blocks are 1 meter
1 meter.
cubed.
Yeah.
Oh,
Nice,
what?
nice.
Yo, he
Okay,
got
can
killed
someone
in
tell
So if you
can
measure
someone
the
tell the
speed at
normal
which
force?
it's falling, you could
Yeah,
if
it's
you measure the speed at which
2,227.
objects fall, you could
Fucking hell.
actually measure get an acceleration value for gravity.
Yeah, you could.
Wait, does
Minecraft is interesting that way.
acceleration, or do they just fall uniformly? Like when you
Accelerate.
I'm about to do an epic. One sec.
Acceleration.
Can we do an experiment to see how fast sand falls? Like, does it accelerate over time, or does it fall at a constant velocity?
Yo. Shit. God damn it.
It has to accelerate, but it probably reaches terminal velocity in like 2 seconds.
Yeah, I'd say something around there.
Well, I mean, does Minecraft have that coded in though? Does it have like?
Probably. We'll check. Let's check right now.
Because otherwise, how else would they deal damage?
Okay, Manuel, we need you to perform a experiment.
Yeah.
Experiment, please.
Hit me. What's the experiment?
So we need to see if Minecraft anvils accelerate or not, or if
Yeah,
they
do
go
they
0 to
accelerate?
Yeah,
100.
they accelerate, bro. Everyone knows that.
How do you know that? Tell me now.
So like drop one from like 2 blocks,
Yeah,
drop one from like 10
it
blocks.
does, it does. Minecraft
It
gravity
does.
has a apparent gravitational acceleration with TNT, snowballs, and everything that like any falling
You
object.
can see by the change in speed. It's so obvious.
Okay,
Yes.
okay, then show us. We want to see.
Okay, I will. See how it
That
starts
looks the
slow and
same.
then it moves fast?
Wow.
Yo,
Okay, I
somebody
think
real quick
Go up a
stop
lot
watching.
higher,
Go higher, go higher, go higher.
Yo, somebody real quick stop watching Adam's
Yeah,
stream.
yeah.
Yeah,
Everyone,
like-
pull out the stopwatch. Let's calculate the time intervals.
Anything, it looks like it just reaches terminal velocity within 2 blocks.
I guess so.
That looked pretty constant, at least halfway
constant.
down.
That did look kind of constant. I'm not gonna lie.
Adam, we're doing.
It accelerated for like
experiments
2
on Minecraft.
blocks.
You're doing. Are you on a Minecraft server right now?
No,
Yeah,
I'm
we're
on a
doing physics
Minecraft world.
experiment.
Just the world, yeah.
We're doing we're seeing if anvils accelerate or not. If so, when do they reach terminal velocity? Seems like 3 blocks in, they reach terminal velocity.
Apparently, according
I
to
don't think
Google,
they're velocity. I think
under
it
5
just
seconds.
goes constant. In my humble opinion, in my thesis.
Humble
Wait, Adam, can you
opinion.
restart your stream? It's like
Anvil,
loading.
what do you, Anvil, Adam, what did you say?
I didn't say anything. I just you guys are in Minecraft? Yes. That's it. That's all.
He said we're fucking nerds.
Yeah.
That's what he said.
No, I support it. I support the
really
science.
bored, alright.
I support the science. Okay, but are we gonna get going
No
on
more Minecraft.
physics
No more
again?
Minecraft.
Yeah, let's get back to physics.
We are
The
learning.
Minecraft
We are
live
learning.
stream now.
Guys, look, I'm in
We are
Mexico. No, I'm not.
We never
Okay,
left
that's-
physics.
We
That's
never
true.
left. We're calculating the
That's true.
time interval of the anvil drop.
Very true.
All the calculations are happening.
Okay, enough of this
Should we-
shitty fucking.
I honestly wish we get a professor to just let us do all our labs in Mine.
Yeah, that's
I mean,
true.
maybe for electrical circuits,
That's true. Hopefully we'll do
because you can actually make.
Somehow that would be way too.
You can actually make
Wait,
gates
I
with
got an
redstone.
even better idea. Let's let Adam start and let's learn this physics.
That's what I was
and we can
about to
talk
say.
about this after the
Damn.
exam.
Any
that's pretty good.
truers?
It's a good idea. Okay, so
Something, because I did not hear anything you say over.
you're cutting in and out. The person talking, so I don't know what you're saying.
Person talking.
I don't know what it is. I don't know the names. Because I don't even see. I don't even have the thing open like with the people's names, so I can't see who's lighting up. Okay, so what did we just do? We just did number 11. Number 11. Okay, we've done 3 questions from static equilibrium so far, but that's okay. We'll make it through. So number 14 is next. Let's see how that goes. Number 14 is here. So there. Okay. So a 10-kilogram monkey climbs a uniform ladder with that weight and that length. The monkey has that weight? No, I think the ladder has that weight. As shown in figure that. The ladder rests against the wall and makes an angle of that with the ground. The upper and lower ends of the ladder rest on a frictionless surface.
Can you guys hear him? Just me?
Can people hear?
Yeah, we can hear him.
Okay, people can hear it.
I can't hear him either. I can't hear him. I don't know.
I wonder if
Sometimes his voice cuts out. I don't know why.
something with the
Like I can see the video.
Yeah, I can
but-
hear everyone now.
I can
Massive
hear him. I
lag.
can hear him.
Okay, I don't know what. I don't know.
It's fine.
Is it? Do you think it's
If you can
me
hear
or
him,
do you
then
think
okay.
it's just Discord?
Just
Wait,
watch.
check which
Guys,
stream
watch
are
the
you on?
stream.
I'm on his
stream
stream.
and
I'm on
listen
first.
to his voice outside of the stream. Like you can watch Sean's, and then just listen to him talk, and you don't need to.
Yeah, my stream has no
Everything
audio.
echoing.
Make sure.
Well, you
the
gotta
person
mute
that is,
mute some of
streaming
the streams if
doesn't
you.
have the thing.
Yeah.
Look bottom right if the volume is up. If it's bottom right should have some volume, and you should be good to go.
For me, That I should check?
Yeah, still a problem. I don't know.
No, for the people who are.
Like I didn't change it since.
Okay, so
Second stream.
I'll write down here. Yeah. Okay, so makes that angle the frictionless surface. The
What?
lower end is connected to the wall by a horizontal rope. Okay. That is frayed and can support a maximum tension of that. Okay. Draw a force diagram for the ladder. Find the normal force exerted on the bottom of the ladder. Find the tension the rope when the monkey is 2/3 up the way up the ladder. Find the maximum distance d that the monkey can climb up the ladder before the rope breaks. And if the horizontal surface were rough and the rope were removed, how would your analysis of the problem change? What other information would you need to answer? Okay.
Boy. Look out of here, boy.
Someone's got their mic
Pop
on.
smoke.
Someone's got their mic on. So let's take a look at part A. Draw a force diagram for the ladder. So the force is acting on the ladder. So, well, first of all, actually, I'll write down the information we know. So the weight of the ladder, I assume that's what that is. The weight of the ladder is 1.2 times 10 to the 2 newtons. Okay. The mass of the monkey is 10 kilograms. Okay. The length of the ladder is 3. Theta is 60 degrees. The force of tension is a maximum of 80 newtons. Okay. Draw a force diagram. So I'll say FT like max is 80 newtons. Okay, draw a force diagram for the ladder. So, well, first let's think about here and here. What's happening here and here? Well, so here is a force of tension going like that. There's a force. There's the there's the force right in the middle. Where's the monkey on it? Nowhere in particular at first. So right in the middle there's that force of gravity. Force of gravity acting on an object. And that's it. So could I just what other forces? The gravity, there's no friction. There's a normal force there. There's a normal force there. Fn2, Fn2. Here we have Fn1. I don't know why it does that. Fn1. What other forces are acting here? That's about it. The force of gravity there. Again, no friction. This is the force of tension. Okay, so from here, let's should it be from one point? I want to see, is the 14, there's no answer in the book for this. Is this enough for that? Draw a force diagram for the ladder. That's all it says. This is a force diagram. It has forces. It's not at one point though, but I think that's okay. Find the normal force exerted on the bottom of the ladder. So find this. Okay. So let's do that. Well, although that doesn't make sense because that's staying put. So there's a force of tension, frictionless. Oh, never mind. Okay. So there's technically, I guess, if I were to combine all of these into one, there's the second normal force, Fn2. There's Fn1. There's Fg, and there's Ft from there. Where in particular is this? I guess it's the whole thing. It's like all the forces acting on it, but they do kind of balance out like this, right? Because this force pulling like this is what's causing that normal force there, because it's pulling it against the wall. This force of gravity is what's causing that normal force. So I think that's still good. So we're looking for the normal force Fn1. Right, looking for Fn1. So let's do our sum of the forces. So the sum of the forces, or should I do torques first?
I just have a question. Is the FG for the monkey, or is the FG for the monkey and the weight of the ladder? Because then you'd have to add these.
That's true. So Fg, this is for the ladder.
Okay,
right?
that's for the ladder. Okay.
So for the ladder, I should put the L there. And then, yeah, there's a monkey on there too, isn't there? So I need to... But we don't know where the monkey is. It climbs. Find the normal force exerted on the bottom. I think we just assume... Maybe let's just assume the monkey's right in the middle. It doesn't actually say where it is. So find the tension, the rope... find the normal force exerted on the bottom of the ladder.
I don't think you need to know where he is for forces.
Yeah.
But would it be?
I'm just saying, like,
Mhm.
I'm just saying that, like, there's gonna be two. Either you combine the force of gravity for the ladder and the monkey, or like you could just say that there's two forces of gravity,
Yeah,
one
that's
for the
what I-
ladder and one for the monkey.
So the thing is, the force of the normal force on the wall, the vertical wall, is the only thing that changes as the monkey moves up and down. The Fn at the bottom of the thing does not change.
Oh, okay. Okay.
I know. I don't see how that's not intuitive to me, but that's just how it is.
Well, I guess, like, because the amount of weight on the ladder pushing down is the same, doesn't matter where he is.
Yeah.
Right? But the amount that it's pushing against the wall does change. Sure. Yeah.
But won't the tension increase too when he climbs up?
Yeah, so that's why it's saying the maximum tension is 80 newtons, and then one of the questions is find the maximum distance the monkey can climb up the ladder before the rope breaks. Right? So...
Oh, okay, yeah, the normal theorem is it.
Yeah. So this is going to be definitely with torques that find the maximum distance d. That's definitely going to be with torques. But I think we can do this one, find the normal force just with the forces. So I think we can just say... Well, isn't it just... what is it? The normal? Find the normal force exerted from the bottom of the ladder. So it's just the sum of the forces in the y direction equals 0. So I guess I'm combining these two into one. I'm saying Fg... Oh, no, it doesn't matter. It doesn't matter. So I will actually do these separately as separate people, as separate things. Right, so there's another
I think it's like last problem. Sorry, like the Sir whatever night a lot. Like it was
Yeah.
different for different places, but in the end of the day, it's just like the sum of them.
Yeah.
and the
So
directions.
so I will draw a different force, but it will be the same thing as if you combine them for this case, for this one part of the question. So I will say this is the force of gravity on the monkey, and this is the force of gravity on the ladder. So the sum of the forces in the y direction, again, if I say that that's my positive and positive, then it is, there's Fn1, that's what we're looking for. And then it's just minus the force of gravity on the ladder minus the force of gravity on the monkey equals 0. So Fn1 equals the force of gravity on the ladder plus the force of gravity on the monkey equals that. So the force of gravity on the ladder is the mass of the... Well, actually, we just know it already. They actually just gave it to us. The force of gravity is 1.2 times 10 to the 2. 1.2 times 10 to the 2 newtons. Plus the mass of the monkey times 9.81. Right? So that's 1.2 times 10 to the 2 plus the mass of the monkey was 10. So 10 times 9.81. 9.81. So 1.2 times 10 to the times 10 to the 2 plus 98.1. Okay, and then that's equals 218.1 newtons.
That's correct.
It's correct? Okay, thank you. Yeah. So that's what I got for the normal force acting up. Okay. Find the tension in the rope when the monkey is 2/3 of the way up the ladder. Okay, so now this distance now from here to here is 2/3. Oops, from here to here is 2/3 of the total length, which is 2/3 of 3. Right? So I'll just say so the distance that he's traveled is 2/3 of 3, right? Which is just 2 meters. So he's 2 meters up the ladder. So d equals 2. And so we'll have to use we'll probably have to use torques for this now. So I'll say my torque is measured from, well, what can I say? I can say it's measured from, I'll just say it's measured from here. Would that make sense? Yeah, I think that makes sense. So what is all the torque that's happening? So we have the sum of the torques is equal to 0. Okay. So what's all the torque again? So these two torques don't count because they're acting at the axis, right? But these 3 torques count. Yeah, and so this is theta, right? That's theta. So first of all, what's going to be positive? What's going to be negative? These two are going to be negative torques. This is going to be a positive torque. So let's start with the positive torque. That positive torque is going to be its distance from the axis, which is the whole length 3. So, well, actually, I'll write it out separately first. So it's the torque caused by the normal force, number 2, minus the torque caused by force of gravity on the ladder, minus the torque caused by the force of gravity on the monkey. That equals 0. And we're trying to figure out, what are we trying to figure out? The tension in the rope when the monkey is, so I can't do that because I need to figure out the tension. Yeah. Oh no, well.
Could find FN2, or do we already know
Oh, that's
FN2?
true. No, that's true actually. Yeah, that's true. I can just find FN2 and that'll be opposite magnitude to that.
Yeah.
Okay, so I'll do that then. So Fn2 is what I'm trying to solve for, the torque, the force there. So I'm going to write down a little lower so I have more space. So Fn2 is going to be its distance from the axis, which is the full 3 meters. Okay, so 3 meters times the force, so Fn2. Okay. Then I'm going to multiply that by sine of the angle between those two things. So the angle between them, oh, careful, is actually this. So it's that, right? This angle here. So it's going to be 90 plus theta. So it's phi 90 plus theta. Okay, so it's going to be sine of 90 plus theta. Okay, minus this torque. So the force of gravity on the ladder, that's going to be halfway up. So it's going to be minus 1.5 times the force. So the force of gravity on the ladder is just W. That's what I call W. Times sine of the angle between those two things. And the angle between those two things is just theta, isn't it? Oh, no, it's going to be 90. It's going to be this angle like that, which is 90 plus theta. Yeah. 90 plus theta. Sine of 90 plus theta. Okay, kind of running out of space. Actually, I'll just move this over. So this here. So minus this one. So FGM. So the force of gravity on the monkey. So its distance is going to be 2, right? So 2 times the weight. So it's mg, mass of the monkey times g, times the angle, which is going to be the same angle. So it's going to be sine. I'll just say times sine of 90 plus theta. Okay, and that equals 0. Yeah, that equals 0, right? So I can just solve for Fn2 here now, right? I know everything else. So 3 Fn2 sine 90 plus theta equals 2 mmg sine 90 plus theta plus 1.5 W sine of 90 plus theta. That's it. Okay, and then just divide everything by 90 plus theta. Sine of 90 plus theta. Did I mess up something then? No, I don't think so. So it's going to be... How is that the same angle up here? That's... Okay, I guess, yeah, that makes sense actually. So it's going to be 3Fn2 equals 2mmg plus 1.5W. So just divide everything by 3. So Fn2 equals 2/3 mmg plus 1.5 over 3W. So I'll plug all that in. So 2/3, the mass of the monkey was 10, 9.81 plus 1.5 over 3 times the weight was 1.2 times 10 to the 2. Okay. So let's give it a try. 2/3 times 10 times 9.81 plus 15 over 3 times 1.2 times 10 to the 2. So I got my force of the normal force there is 665.4 newtons, and so it's equal and opposite to this. Well, I guess it should be negative.
Wait, did you say 15 or 1.5?
Oh, I said 15. Thank you. So I got not that. Well, factor of 10. So 125.4 newtons. And so that's Fn2, Fn2. And so Fn2, the magnitude of that is the same as the magnitude of the rope, because they're well, I could quickly do the sum of the forces in the x direction equals 0. So what's in the x direction? Force of tension minus the force of the normal force. So the force of tension is positive minus Fn2 equals 0. So Ft equals Fn2. So therefore, Ft equals 125.4 newtons. Is that right?
I think it's 72.4.
Okay, so let's see what happened. Did you do the same thing as me to get that, or did I just plug something in wrong, or did you do something else?
Oh no, I just saw the answer.
Oh, you just saw the answer. Okay. So, let's see what we're doing. So tension of the rope on the monkey is 2/3 the way up the ladder. The ladder is 3 meters, so 2/3 are 2 meters up. Okay. Sum of the torques. Unless this isn't equal and opposite. No, there's no friction. That goes like that. That goes like that. So, you think what? Sorry? Someone said I think something, but I couldn't hear the end of the sentence. Well, I think Discord is struggling.
I didn't hear anything.
Okay. Am I still like, Manuel? Am I like for you? Am I still like clear and I'm not like breaking up?
Yeah, you're good. You're
Okay.
good.
Okay.
Yeah,
So,
you're good.
Good. Just want to make sure. So, yeah, let's see what happened here. We're 2/3 of the way up the ladder. So yeah, that's right. Am I missing a force here? Don't think so. So I did the torques. The torque from there, torque of Fn2. That's trying to pull us that way, so that's negative. These two torques are also trying to pull us that way, so those should also be negative. Oh, hold on. Wait, why is this? Oh, no. That torque is pushing us. This force is pushing it that way, so it's positive. And so positive, negative. These torques don't do anything. I know those forces are equal. So the torque of that of Fn2 should be 3 times the angle between those two tail to tail. So 90 plus theta. That's right. And then 90 plus theta minus 1.5 W, which is also 90 plus theta. 90 plus theta and 90 plus theta. And this is 1.5 is halfway up the ladder. Minus 2 is how far up the monkey is from the ladder. Also, sine of 90 plus theta. Divide everything by 90 plus theta. Am I allowed to do that? Looks like it. So 3 Fn2. Yeah.
Hello?
Hi.
I think you're supposed to write Fn 3Fn2 sine 60. So that angle is different. Because
this would be
it's
60?
Yeah.
The thing is with that is that that's not the formula is said it's like it's the angle between the vectors tail to tail, right? So the radial vector goes like that, tail to tail it would make that angle there, that theta.
Okay.
I used sine. Oh, sorry.
Oh no, yes, she's right. So the angle, I think it might be you know how you said 90 plus theta?
Mm-hmm.
I don't think it's 90 plus 30. Like if you do the geometry, like the
Yeah, 90 plus 30. Oh, okay. Oh,
angle?
yes.
Yeah,
That
yeah.
is theta. Yeah. I see. Okay. So I just did. Yeah. Okay. This angle here is theta. This angle. Let me draw it a little. Well, it's kind of gonna be hard to draw in a separate spot. So let me erase this top part, and I'll do that again. So we have our normal force going like that. Okay. We have our radial vector going like that. Okay, radial vector going like that. I'm trying to figure out what this angle is. So that's what I need. I know that this makes a 90-degree angle. I have to figure out what this phi is here. I know that this angle here is theta, right? I know that angle because of the rule, right? The F rule. And so we can say up here that we know that phi plus theta make 90. I know theta is 60 degrees, right? So phi must be 30. So yeah, that's what it is. So then I can't. Is it the same for these ones too? No, these ones are theta. These ones are theta. Yeah. Okay, so I can't do all this division because this one is 90 plus phi, which was 30. So 90 plus 30. So I'll just write it here. 90 plus 30 is 120. So then this is also 120, and now I have to erase all this. So let's see here. Erase all this. Okay, so now I still want to rearrange for that though, right? So I'm going to say 3Fn2 equals 2mmg sine of 90 plus theta plus 1.5w sine of 90 plus theta all over, well, I guess I can get rid of that too, all over 3 sine 120. There you go. So I will plug that in, right? So mm is 10, g is g, sine, I know everything else. W is 1.2 times 10 to the 2. So this is going to be 2 times 10 times 9.81 times cosine of 60 plus 1.5 times 1.2 times, 1.2 times 10 to the 2 times 10 to the 2 times sine of, or times cosine of 60 over 3 sine 120. I got 72.4. Was that the answer?
Yeah, that's it.
Yeah, there you go. So yeah, okay, that makes sense. So that was the mistake I made. I even said when I was doing it, I was saying, why is it strange that they're all 90, but then I thought I worked it out, but no, that's not working. Did not work out. So okay, there's that. That was part C. Now part D is find the maximum distance that the monkey can go up the ladder. So it's pretty similar to the last question. We just want, we want to know what is the distance up the ladder when the normal force is equal to 80, right? When this normal force is equal to 80, because then this tension is equal to 80, and that's when it'll break, right? So I guess that would be the maximum height when that's equal to 80. So we take this same equation, I'm pretty sure. We know that's 80, and we're solving for this distance here. So I'll take this again. I'll just take this. So we're doing the sum of the torques. Just doing the sum of the torques there. And I'll also take this equation. Well, I guess I don't need that 0 there, do I? But it's fine. And I also want to make sure I'm there, yeah. So there's that. And so we know this is 80 now. We know that this is 80. The force, the normal force is 80, okay? We're solving for this distance D. And that measure, that D is going to be the height when this is 80. And it should be, if I'm assuming everything correctly, that is going to be the height of, like where the thing will break. So 240 sine 120 minus 1.5 w cosine theta minus dmmg cosine theta equals 0. So we're just solving for that guy, right? So it's just going to be 240 sine 120 minus 1.5 w cosine theta equals dmmg cosine theta. And of course, just divide both sides by cosine theta and mmg. So it's going to be, well, I'll just do it here. So divide by mmg cosine theta. So that goes away, and I'll just plug everything in. So 240 sine 120 minus 1.5 cosine of 60 over 10 times 9.81 times cosine of 60. So I got, that doesn't make sense. D equals 4.2. The ladder is 3 meters long, so it doesn't make sense. So I should work this out better.
I think you forgot to multiply the W with 1.5.
Ah, yeah.
Like 1.5 W.
Yeah.
Yeah.
1.5. Yeah, I did forget to multiply that. Times 1.2 times 10 to the 2. And now I got 2.4. Which I think makes more sense. I don't have an answer. If someone has an answer, is that the right answer?
Yes, correct.
Okay, good. There we go. So that's the maximum height. And are we supposed to do every part of this question? Oh yeah, actually I have the answers here too. And then E is, if the horizontal surface were rough and the rope were removed, how would your analysis for the problem change? What other information would you need to answer C and D? Well, we'd have a force of friction, obviously. We'd have force of friction. We need to know the coefficient for the friction, and we need to know... that's pretty much it, because you take away the rope, so yeah, that's all you need to know. How would your analysis change? Just like you'd be doing different forces. Not much of an answer for that one. And yeah, that's what they say here too. Okay.
Would there be friction where the normal force is for number 2 force? Normal force 2.
Yeah, there would be friction there too. There would be friction there too. Yeah.
And there'll also be
Because it's a surface touching, right? It's a surface touching there, so there would be friction.
Sorry, Adam. Can you once again explain where did we get the 120-degree angle from?
120-degree angle. Let's see. Where does here? 120-degree angle here. That's in here, right? 90. Wait, hold on. No, that's in here. This is the 120-degree angle. Yeah. So we're pretty much looking for. Can I zoom in? Is it gonna let me? Kind of. Whoa.
Oh, nice.
Okay. I think I can just move over. Hold on. Come on. It doesn't let me scroll. Oops. No, don't want that. Okay. Let me go back to normal view. There. So. Oh, wait. Oh, it sent me way up?
Oh.
Okay, there we go. So, up here, right, we're looking for, I'll draw the ladder a little bit better. There's the ladder, right? There's where it touches the wall, right? There's the normal force coming out of it, right? And so we're trying to figure out the torque done by this force, right? That's the force, that's the ladder. So the radial vector that comes from the axis down the ladder, it comes out like this. If I were to put a tail to tail with the force vector, that's our radial vector, right? So I need to find this angle in here. That's my phi, okay? Or that's my, yeah, I'll call that my phi, okay? So to find that angle, I know that this is going to be 90 degrees here, right? And I know that it's going to be 90 degrees here too, on this side, right? Like that. So one thing I know from the question is that this is 60 degrees. So this must also be 60 degrees, right? If that makes 90 degrees, then this must be 30. So then this must be 120.
Oh, I see. But why
Right.
don't we use a 60-degree angle in the first place?
Because we need to know the we need to know the angle between the radial vector, right? The radial vector and the force vector when they're tail to tail like this. Right?
Oh,
So
tail to tail, right?
Tail to tail, right? So they need to be like, I guess, could you use this? I guess that might be the angle probably works out to be the same thing.
Yeah.
With the sign.
But, okay. So, but why the radial vector is pointing outwards? Shouldn't it be pointing to the inside?
Like, you mean like should it be pointing like this here?
Yeah.
But
no. The other way.
Pointing like
pointing downward.
Here?
Yeah.
But our pivot is here.
Like
our pivot's here. The center, the axis of rotation's here. Right?
Okay,
so it'll come. It always comes from the axis of rotation.
Oh, I get that.
Always comes from the axis of rotation. So then I have to. So it's really like it's like this, but I move it up to put it tail to tail, and then that's where I calculate the angle.
Oh, I understand. I see.
Right.
Thank you very much.
No problem.
Hey, can I see what you did for B again? Just with the normal force?
B is the normal force thing? Yeah. So I did
some of the forces. Why?
Isn't it just this? Yeah, it's just this, I think.
Yeah, that's just some of the forces in Y, and then you just equated for N1. Okay.
Yep. That's it. There you go.
Okay, thanks.
Okay, that one wasn't too bad. That one we made it through. 26 is next. So 26 is here. Do I need more to it? Yes, I do. Okay, so 26. There's two pictures I need to take for this one. Two pictures. So there you go. So there and there. So in exercise physiology studies, it is sometimes important to determine the location of a person's center of mass. This determination can be done with the arrangement shown in that figure. Okay. A light plank rests on two scales which read that many newtons at a distance of that separation. How far from the woman's feet is her center of mass? So, okay. So we don't know the mass, but we assume it's a light plank. Okay, we know it's a light plank. Let's say or I guess since we don't know it, let's put the center of torque here. Okay. Might have to use. Okay. So the center of torque is there, like the axis of rotation is there. So what is the force applying down onto these scales here? There's a force of. It's pretty similar to that thing with the people carrying the pole. It's kind of the backwards way of this, right? So 1.65 meters apart. Torque is there. So the force down here, or the force down here is 380 newtons. The force down here is 320 newtons. So then the net torque is 0. Okay, net torque is 0. Both of that, well, no, one of them's positive, one of them's negative. Okay, so the torque for FG1, so I'll say FG1 minus the torque from G2 equals 0. So the torque from G1 equals the torque from G2. Now, how does that help us find our center of mass?
Should we put the pivot on one of the sides?
Put the axis thing here?
Yeah, wouldn't it be easier since you just have one being 0, basically?
Sure, yeah, okay. And then we also have then we have a force from her center of gravity. Yeah, then there's also a force from her center of gravity. I'll say it's like right there, right down. And is that a normal? This is a normal force up then, isn't it? I think this might be right. If I say the normal force is going up.
Yeah, they should be up because of the new block.
Yeah, that makes sense. Okay. So then the net torque is going to be, for this one, it's going to be negative. This one's going to be positive. This one is going to be, oh no. Yeah, this is going to be 0. Never mind. This one's going to be positive. This one's going to be negative. So the positive torque is from that 320 newtons. So the torque from G2 minus the torque from the center of mass equals 0. So the torque from G2 equals the torque from the center of mass. So let's figure out the torque from G2 equals the distance from the radial, from the axis of rotation, so 1.65, times the force, right, times sine of the angle between them is just sine of 90, so that's just 1. Okay, so the torque from the center of mass is equal to its distance from the axis, r, times the force. The force is going to be the sum of these two forces together, right? The force of that is going to be 320 plus 380 times sine of 90 is 1 again, right? So I think now I can just say 1.65, since I said over here they're equal. 1.65 times 320 equals r times 400, 700. So r equals 1.65 times 320 over 700. So it's going to be 1.65 times 320 over 700. So I got 0.75 meters, which makes sense. And is that the answer?
Yep.
Okay, good. That wasn't too bad.
So why doesn't the normal force cancel out or equate the second FG2 to be 0?
Why would it be? Wait, why would it be 0? This FG2.
Because isn't the normal force equal in magnitude in opposite direction?
Yeah, equal in magnitude to this, to here, to this. These two normal forces combined are equal and opposite to the gravity down.
Should just write the net force in the y direction.
Yeah.
Oh, you would. Oh, okay, so it would only be in the upward direction, not the downward.
Right. Yeah. So FG2 plus FG1 equals equals FG from the center of mass.
Oh, okay, I got it wrong. I was thinking that there's 3 downward directions.
No, yeah, 2
up.
of them are up. Yeah.
Okay.
Well, Adam, apparently the answer is 0.896.
Oh, okay.
Yeah, I was gonna mention it because this is the distance from center of gravity to her head. You should find it from center of gravity to her feet, so that you should
how far
find
from the woman's feet is her center of gravity? Okay,
Her
so then
feet, yeah.
I should have just
1.65 minus 75.
Yeah, so the answer is 1.65 minus 0.75. So 1.65 minus 0.75 is, well, I got 0.9.
Oh.
No, it's 8957 something like that.
Okay, so that's fine.
But wait, why did we subtract it? It was from
her feet. It's supposed to be from her feet. So if we know it's from here to here is that distance, it's going to be the whole thing minus this.
One question.
Yeah.
Just one question. Why did you pull a torque calculation in the first place?
Completely glitched out there for me. Can you say that again?
Sorry, why did you pull? Is that a torque calculation in the first place?
This torque here? Yeah. Well, because
why do you pull torque in general?
Well, because the unit is torque, so I know I'm gonna have to use that, and because there's not like an even. It's not evenly, like if she was right in the middle and that center of gravity was right in the middle, right? Then it would just be even on the both scales, right? So I know it's off to one side.
Wouldn't you just use the center of mass calculation point?
So the center of mass, like you mean like calculate the x value, like the RCM, by doing 1 over the total mass? Is that what you mean?
Yeah,
Like,
that entire calculation of 2 points and the distance between them.
But you don't really know the distances, though.
Yeah, you do. It's
Exactly,
one.
yeah.
They gave you the distance between them.
No, but she's not uniform. Her mass is spread differently. So you can't do the divided by the
that's
total mass.
true. You would need to have every point.
Yeah, I was gonna ask. Like, I was gonna say, like, alternatively, why we couldn't just do 1.65 times 380 divided by 700. But I guess it's just like from whichever point you take it from.
Yeah, it's from whichever point you
Oh
take
wait,
it.
if the mass is distributed unevenly, wasn't there something about taking a limit for that?
Well, say that again. Sorry, you keep cutting out for some reason. Sorry.
My computer's crap, but couldn't you take a limit if the mass is uneven?
Well, yeah, but then you'd be integrating, and we don't do any kind of integrating in physics right now, at least. Right? Yeah.
Fair. Okay.
Yeah.
Why did you subtract by 1.65? Like, what was R that we found? Was that
R was this distance here. But we're looking for this distance here.
Okay.
One question.
So if you made the if you made the axis to be on the feet and then calculated from there, then you wouldn't need to subtract, right?
Exactly. I wouldn't need to subtract. Yep. I should have
Alright,
seen that
thank you.
when I should have seen that when I read it, but I didn't.
Yeah. My question was just originally you had like the torque was T1 minus T2. Why did you switch it again to T2 minus T1 in the beginning equals 0?
Because originally my center of gravity was right. I mean my center of the axis of rotation was here. I chose it to be there, but then I decided no, I'll put it here so we get rid of one of the forces.
Oh, okay.
Right.
That makes sense.
Yeah.
Thanks.
I have a question.
I was just wondering, like, why did you do like 320?
Is someone asking something?
Yeah, someone's asking something. Sorry, can you say that again?
I'm asking, like, why did you, like, to find the torque of center of mass, why did you add, like, 320 plus 380? Like, I don't understand that.
Because the torque of center of mass is defined like this. Okay, so it's going to be the distance from the axis, right, times the force of that thing, right, times sine of theta, right? But we know up here that, this equals the torque Cm, right? That force is just the force of gravity from the center of mass, right? And we looked at here from some of the forces in the y direction, that's just equal to the two forces they give us.
Okay, that makes sense.
320 plus 380. Yeah, no problem.
Okay.
Are we gonna like do all the examples on this particular topic, or are we gonna like start with the older topics now or something?
Yeah, I guess maybe let's. I was thinking that because we are like we're at the last hour, so do people want me to just start doing practice exams, old practice exams? Because I can do that too.
Yeah, I got a couple questions that are kind of.
Can we do practice exams?
Okay, I think that's a good plan. So
could you quickly just scroll down a bit?
I
sent you a
Thank you.
3D torque question, which was kind of difficult, and I got a few people getting different answers.
I could try it, but I don't know if I'll be able to do it. Let's see. Yeah.
It's a 3D torque question.
Yo, I think we.
The answer that we just got. Can you explain why TG2 or the torque of G2 minus the torque of the center of mass is 0?
Well, those are the only two torques that are applying, right? So the net torque is 0. So what torques are applying? This torque, but it's 0 because it's at the axis. So that doesn't count. Then it's this.
Is the thing in the middle?
No, it's at the end here. It's that red dot there.
Oh, okay.
That's where that.
Makes sense.
Okay, there you go. Sorry for the hammering. There's just like people building things here. So 3D torque question.
Yeah, I'm sending some in discussion.
Okay. Oh boy. So
yeah.
What? There's no way that's on the exam. What?
It was on. I think it was 2018.
So I'm looking at the pipe one. Yeah, I don't think they're gonna give us a question like this on the exam, but
Yeah, I really
If they
hope
do,
not.
it's over. But whatever.
It's really easy though. That's the thing.
Is it?
Yeah, like they look complicated, but it's all just about equilibrium. It's just all about Newton's laws.
Yeah, that's true. Okay, let's try this one, I guess. Let's see what happens here.
Physics kind of do be like that.
Okay, here. Let me just think it better. Don't know why
It's
that
all
screenshot's
based
doing
on
this.
like 3 things.
Yeah. And they're all called Newton something. So, yeah. Okay, there you go. The pipe assembly is subject to a 80 Newton force where that string, that pull thing, okay, determine the moment of the force about point B. The moment, as in like the torque. Okay. The torque of the force about point B. Okay. Well, the
answer for this question is C.
Okay.
Sorry, I just highlighted it.
Yeah, I'll put it there. That's the answer. So, well, okay, so torque is equal to the vector is equal to the radial vector times the what was it? Force vector. Times the force vector. Yeah. So let's find the force vector we know, don't we? Pretty much, we can find it. Radial vector, it will just be from B to C. What's the radial vector? Okay, well, we can do that. So what's the x component? So let's start with that. What's the radial vector? What's the x component of the distance from B to C? So it's just how far along this way is it? So it's 300 plus 250. And I know that's in millimeters, so I'll switch that after. The y component is 0. And the z component is going to be negative 200. Okay, that's our radial vector. Then our force vector is going to be, the x component is going to be, okay, first let's look at this triangle in there. Let's look at that triangle in there. Okay, so that's 80 newtons like this. This is the force in the z direction, force in the xy plane. Well, it's not a vector actually, it's just a line. This angle is 30 degrees. Okay, so we can find the force in the, well, let's find the force in the z direction first. So the force in the z direction, that's the right angle, is going to be sine. So it's going to be 80 sine 30. Okay, and the force in the xy plane is going to be 80 cos 30. So now let's go back to this triangle up here. That's going to be like that. And it's going to look like this. That's a 40-degree angle. This is our this is our fxy plane. This is our fx. This is our fy. Right? So then so we know our fz. So our fx is going to be fxy sine 30, sine 40. And our fy is going to be fxy cos 40. There. So we know our 3 components now of the force vector. Right? So I guess I'll just actually compute it, like put the numbers in. So R, I'll just do that. So 300, so 550. So that's just 550. F is going to be, so the x component is that times that. So the x component of F is going to be that 80 cos 30 times sine 40. The y component is going to be 80 cos 30 times cos 40. Oh, someone's knocking. Hold on 1 second.
It's the cops.
So, how's everyone doing today?
Force is 80 Newton. So confused.
Yo, is the
I'm
force?
so.
Yo, are you
So
no one's
this
gonna?
isn't like CEN, you
said
know.
hi
You're
to
not
Saul.
talking to Uma, you know.
Yo, yeah, where is Umski?
People confused about what I'm doing?
Yeah, just
A little
a little
bit.
bit about the angles and the triangle and all
Okay,
that good stuff.
let me
You start
just put the z value, and then I'll explain in just 1 second. So the z value is 80 sine 30. Okay, that's our force. And then to find the answer, you just cross product these two. So, okay, so what I did is that I took this triangle, this green triangle. Oh, well, I erased it by accident, but this green triangle, and drew that here. That's this green triangle. Okay, so that's an angle of 30. That's the F on the XY plane, that line right there, right? Should be a 90-degree angle there. That's the Z component, Fz. And I know that it says the force is at magnitude of 80 newtons. So that length is 80 there. So using just trig, I can find Fz, which I did. And I can find Fxy, right? And now that I have Fxy, I know this length here. I know this purple length all the way like that, right? That's the same purple length as that, right? So if I know that, that's going to be the same purple length as this on this triangle, on this one here. So I use another color. It's going to be this red triangle. It's going to be that right there. So again, since I know this length, I found it, right? It's equal to this. Well, I can just use trig again to find fx. That's an x there. It's black. Fx and fy. So now I have all my components. It's just going to be a multiple of fxy. So then when I put it actually in, I replace fxy with this. That's what I said it was. So it's going to be 80 cos 30 sine 40. Then 80 cos 30 cos 40. And then the z component is from up here. We found the z component there.
Someone else.
Okay, that makes sense. I got a question really quickly.
Yeah.
How'd you get your r vector? Was it just those pipes combined?
R vector, yeah, it's just the distance. I'm just trying to find the distance from here to here, right? So I just do component by component. The x component is going to be 300 plus 250, right? The y component is 0, doesn't move this way, right? And the z component is going to be negative 200. Goes down.
But wouldn't the y component be 400 because it's 400 millimeters off of the original axes?
We're looking from B to C. We're looking from B to C.
Okay.
That's all we're looking for, because it says determine the moment of the force about point B.
Hey, sorry to interrupt. Can somebody in Adam's lecture leave so we can stream it again, guys?
So while you were explaining everything, I've just started to stop working.
Because Sean left, and now they can't see anything.
Oh, really?
But
Okay.
it's full, so nobody's leaving.
So someone
leave and then watch my stream. There you go.
I left.
Thank you.
Okay, thank you.
Great. Awesome.
There.
Okay, we're good to go? We're good? Like it's...
Yeah, everyone just
Can
joined
you just
mine.
explain how you know that, what line fxy is? How'd you get that?
fxy? Well, I just did, right, I'm just looking at, so I looked at that green triangle in there, right? And so I just did 80 cos 30, right? Because it's the adjacent side, right? So because, right, cos theta is adjacent over hypotenuse. So adjacent over hypotenuse. So cos theta.
We have to assume that is xy, fxy.
Well, we know it is because, like, and I'm just calling it that. It's just that line there. It's just the component in the xy plane. And from that, we can find... It's like the projection, pretty much. The projection onto the xy plane.
Okay, that makes sense. All right, thanks.
No problem. Someone's whacking their microphone.
Why is like for the R BC, it's like 500 550 and then 0 and then negative 200. I don't get why it's 0. Like why it's just not, we're assuming that it's not moving in the y direction, or there's no displacement in the y direction.
It doesn't move. It's not like the pipe is like over here, right? It's not like you go like this and then up and like, well, it's kind of a bad drawing, but not just kind of, it is a bad drawing, but the like, yeah, it doesn't give us any numbers also on like how it moves. And you can kind of see from this, you see it like it just follows this line, then down, then more this way.
Okay.
Right, so no, it's not moving in the y direction. I'm just also bad at drawing, so yeah. Last thing is we need to also convert this into meters, right? And you convert that all into meters. So let's get that. Okay, so that's our force vector, our radial vector. Radial vector is That in meters, so millimeters, so that's 0.55 meters, 0 and negative 0.2 meters. And so we just take the cross product of these two. But I'll actually just turn this into decimals because it'll be a little easier to just write. Although I usually don't, but in this case I will. So cosine 30, sine 40, 80 cosine 30 sine 40 is 44.53. 80 cosine 30 cosine 40 is 53.07. 80 sine 30 is 40. Okay, so now we take the cross product. So it's R cross F, right? Or is it F cross R? I think it's R cross F. Yeah, it's R cross F. What'd you say?
Yeah, I think it's cross F.
Isn't it always R cross F? Like, when has it not been R cross F?
Yeah, no, I'm just trying to remember which way it is. So it's R cross F. Yeah, we're good. It is that. It's never not that, right? So R cross F would be 0.550 negative 0.2 0.55 0 negative 0.2, and then we're crossing that with 44.53. 44.53, 53.07, 40, 44.53, 53.07, 40. So determinant is going to be 0 times 0 minus this. So the first component is going to be 0.2 times 53.07. Next one is going to be, well, a little bit more complicated. So negative 0.2 times 44.53 minus 40 times 0.55.
Doesn't that say 84.52?
No, 44.
It's 44. It just looks like an 8, I think.
Where, here? This one? Yeah, that's a 40. That's a 40, yeah. And then this one is going to be 0.55 times 53.07. That's it. There's a 0 there. So it doesn't matter. Okay, and so then working this all together, that should be our torque vector. Is 0.2 times 53.07 is 10.61. Negative 0.2 times 44.53 minus 40 times 0.55. Wait, did I do that right?
With the 40 being negative?
Well, yeah, it would be negative because it's this minus this. Right, so that's, yeah.
No, because on the forces, it's going down the z-axis. In the drawing?
Oh, you're right. Yeah, I didn't think of that. Yeah, you're going down. The rest of them are positive. Yeah, you're right. The z component is negative. So the z component is negative. So the z component is negative. And that's the only thing that affects it. And so this would be that's still 0. That's positive. Yep.
Where did you get 0 from?
This 0 up here?
Yeah.
From the y component of the radial vector.
But it is moving in the y direction. I mean, it did move in the y direction, right?
Well, no, it didn't. Because like from here to here, you don't move in the y direction to get from B to C. You don't move at all in the y direction.
He made B his origin point, I guess.
Well, it tells you to do it. It says determine the force, the moment of force around point B. Right.
Just move it on A. Yeah.
Yeah, we're not around point A. We're around point B, right? Yeah. So.
Explain how you got the components for F again.
Yeah. So, components for F is there's these two triangles here. There's these two triangles, right? So first I took that bottom triangle out. So the bottom triangle it's the green one and it has that purple line on the top, right? So I know this angle is 30, it shows in the picture. I know this length is 80. So just using trig, I can solve for Fz. which will be the negative of that, right? Because it's a negative direction. Then I can also solve for fxy, that purple line. So that's not really one of my components, but it'll very much help me in the next step of getting my components, right? So the next step is to look at this red triangle, also with the same purple line, fxy. And from there, I know that angle is 40, shows in the question. So I can, again, just using trig, I can solve for fx and fy in terms of fxy, right? Using this line here, that thing. And then when I put it in here, I just substituted fxy for 80 cos 30. So
can you show the picture of the pipes for a second?
Exposition negative.
Okay.
Is point B the bottom part?
Point B here?
I'm blind. Okay, it makes sense.
Good. Okay. Sounds good. So so far it's 10.61, close enough to 11, I guess. Then let's see the next one. Where am I going? Here. So it's just plus instead of minus. So this is going to be 13. And then it's going to be 0.55 times.
Why are you adding? Shouldn't I be subtracting?
Here, let me just put this number down and then I'll explain. So 29. Don't worry. 29. Let me just make sure that's right. So 11, 13, 29. Yeah, okay. That's pretty much. So I'm subtracting because the z component is negative, right? Z component is negative. So it's going to be negative here, right? So this is going to be negative. The actual, when I do the actual math, it's going to be negative here. So when I put it into the doing the cross product, it's going to be a negative 40 here. So when I find this middle term, it's going to be this times this, which is negative.
Got it. Yeah.
And then minus this times this, which will be positive.
Yeah. All right. Thank you.
And there you go. So this top one's slightly off because it's just supposed to be 11, but it's just like a rounding error. That's fine.
Question: is it that the can you go to the z axis, like the first there?
Here.
Yeah, a little bit more. Yeah, x, y, z. That's what's negative, right? Or is it the when does the negative come in? Like,
well, just looking at the picture here, the z is going down. We're going down, right? Like the z axis. The z axis is positive up this way, right? It says it's up.
Yeah. Oh, yeah.
Positive y, positive x. So the moment we're not heading, the moment we're heading down, straight down, that's this negative z, and so we are doing.
Yeah, and so because that's negative, then that was like scroll down a bit, please. Yeah, that's good. Okay. Yeah. Okay. Thanks.
Good. Okay.
Yeah.
Do you think this is gonna be on the exam or no?
Well, we did do 3D vectors at the start of the class, at the start of the course, so I wouldn't be surprised if there was a 3D vector question.
Just go with CGAT.
Yeah. But yeah. Okay, there's that. So we have half an hour left, so what questions should I do for the last half hour? If anyone has suggestions. Should I do another 3D one? Because people sent 3D questions in the chat.
Rotational kinematics.
Sure, if you have a question, maybe try to find a question for me and send it to me, and then, yeah. Or if people have any kind of questions, even from just like regular kinematics or from vectors.
I think in Tornov's, Professor Tornov's last thing, he was saying something that we need to show we know the difference between something on an incline versus like for like bank, like when a car is going around like a corner.
Yeah.
He was like making assist on something like that. So we might get a question like that.
Yeah, that's 6.1 material. Yeah.
Because I remember him showing like two pictures. One was just a car going down, so it's just treated as a point mass, and the slope it's on. But then he was like, make sure you know the difference, and he showed like the bank car thing on the right with the static coefficient. Sorry, kinetic. What was kinetic? Was it? No, static because it's not sliding or something like that.
I'm sending my bank
You're setting something?
Okay, yeah. In the meanwhile, can you just scroll up and I'll just like look at this thing one more time with one more time. Scroll up, yeah.
Here?
Yeah.
Guys, I had a quick question.
Yeah.
Is the like a rotational kinetic energy part of the test?
Rotational kinetic energy, yes. Oh, rotational kinetic energy.
Yeah.
No.
Like delta K and delta U in rotation.
In rotation?
That's not right.
I don't think so. We never did a question like that.
Yeah. Okay. Thank God.
Yeah.
Down to 3.
Oh, voice cutting out. Couldn't hear you.
Yeah, it faded.
Could you say that again?
No, but like the exams at like 3, right?
3.
Yes, like
Yeah,
3.
because somebody said 3.5 hours, and I was like, "There's no 3.5 hours to the test."
No. I meant like 3.5 hours till freedom.
Oh, okay.
Yeah.
Oh god, so here,
Shao really
wait.
wants to like be free.
Yeah. So. Yeah.
Are we looking for questions?
Yeah, I'm looking at some questions that someone sent me. So there's one question here. I can try this one. So here we have this. Let's give it a try. The figure below shows a mass of 1 kilogram moving with constant speed in a circle of radius that. What is the angular momentum of the particle with respect to point A when the particle is in position, where the position vector makes an angle of that with the horizontal? Ooh, okay. So the angular momentum is like it says there. The angular momentum is the radial vector crossed with the momentum vector, the linear momentum vector. Linear momentum vector, since mass is 1, is just going to be equal to the velocity vector. So, well, what's the radial vector? The radial vector is going to be, the circle has a radius of 20 centimeters. So we just need to figure out the x and y component. So the y component of this height, we know this is 20. So this distance is going to be 20 plus 20 cos 35. That's going to be the x distance, we're talking about the radial vector right now. The y is going to be just 20 sine 35. Right. Okay, so there's our radial vector. Our momentum vector is just going to be, again, the velocity, because mass is 1 again, right? So what's the x velocity? What's the y velocity? Let's see. What are some other things we have here? So what are we looking for? Oh, the k, the angular momentum. Yeah. Circle radius. What is the angular momentum when the particle is shown in position where the position vector makes an angle of 35 degrees? So the velocity here has, can we figure out any of the angle that it's going at right now? I think we can, can't we? This would be 90. So I want to figure out the angle. I want to figure out this angle here. I think that's 35. Because if you were to bring the circle down, if you were to bring the circle down to the axis, it would be 0. So it would be just straight up. Okay, yeah, that's 35. So the velocity, the x component of the velocity, which is in this case the same as the momentum, again, because mass is 1. So let me write here. The radial vector has a x component of 20 plus 20 cos 35. Y component of 20 sine 35. So that's our radial vector. And then I want to take the momentum vector, which is going to be the x component of the velocity. So the x component is going to be 5. So I do notice that I have to switch these actually to. This is in centimeters. So I've switched to meters. But it's going to be 5. What did I say? X component first. So 5 times sine 35. 5 sine 35. And the y component is 5 cos 35. Oh, 35. And yeah, so I just need to turn this into meters. So just to turn it into meters is 20 centimeters. So it's 0.2 meters, 0.2 meters, 0.2 meters. And so now we just take the cross product. But cross product is only defined in R3, so you just stick a 0 at the end of all these. So
Oh, wait, can you go over the angle for the momentum again per sec?
For here, well, it's just it'll just be the same as this angle. Will be the same as this angle. There's some geometry there, but what I do is I just sort of imagine if I pulled this back down to meet the x-axis, this angle would be 0, and this angle would shrink just as fast. Right? Imagine if I'm pulling it down, this angle is shrinking just as fast as this angle is shrinking. Right? If I were to pull it down, so they're the same angle.
You know when you do that dotted line, we know that's like 90 degrees, right?
We know this is 90 degrees. Yeah, this is 90 degrees here. We don't know this. This is some angle. This is 35 degrees.
Okay. I feel like it should be 60 somehow. Because
well, let's see if we get the right answer. Let's see if we get the right answer here, and then okay, let's see what happens. So it's going to be 0.2 plus 0.2 cos 35. 0.2 sine 35, 0, and I didn't give myself enough space. I'll just write it smaller. It doesn't really matter. I'll just say x here. 0.2 sine 35, 0. X I have to write this time. 0.2 plus 0.2 cosine 35, 0.2 sine 35, 0, and then 5 sine 35, 5 cos 35, 0, 5 sine 35, 5 cos 35, 0. So it's 0, 0, 0, 0. So the x and y components are both 0. Okay, and all I have left is this times this minus this times this. So 0.2 plus 0.2 cos 35 times 5 cos 35 minus 0.2 sine 35 times 5 sine 35. So I got 1.16. And is that the answer? 1.8. Oh, 1. Oh yeah, so never mind. 1.2 is what I got, which is not the answer there. So yeah, maybe that angle's wrong. Okay, here you go, 1.8. What did you do differently? Let's see. 180. So this is 180. This angle is 90. This angle is 90. Wow, so many lines on the one drawing. Let's erase what I can. So
there's a there's a 20-degree angle. I don't know how we found that.
Where's the 20-degree angle?
Didn't you just write like a 20-degree angle?
Just the angles were all 35. The 20 was from the length here is 20 centimeters. The radius is 20 centimeters. This radius is 20 centimeters. So what I'm thinking is, okay, this, no.
I think the angle is right.
You think this is like this should be 35?
Yeah, like so the way I looked at it was like that triangle, the bottom of 35, like we'll make a right angle triangle on the there. You can find that top right angle, right?
Where did it go from there? Because you know that that's 90. You can find the top right angle, and then and then like on the left side of like the black arrow, it'd be a 90-degree angle. So whatever angle you find plus there, I forgot. I don't know. I remember
No,
like
the angle is
just
definitely correct. I just did it in my notebook. It is correct because like there's a bunch of 90-degree angle that you can just do 90 minus this, right? The angle is definitely correct, but we're messing up somewhere else. But see, they have a 17.5, which is half of 35.
See, that angle is not 35. Like, I feel like
I think someone said that you're supposed to use radians because it's in a circle or something like that. Because angular stuff is always in radians, not in degrees.
Well, okay. I don't know if it'll make much of a difference though, because all I'll be doing is okay.
It wouldn't. It'd
Someone's
still give you
knocking
the same
again.
posting.
1 second, sorry.
So wait, where's this
how
question?
is it?
Can someone say the entire question? Hello?
What
Hi.
was your question?
Where'd you guys, where's this question sent? I need to get a picture of it.
I don't think he sent it. Just a screenshot after, or once he starts it.
Manuel, I got a question. Can you give me back my reactions in general?
Yeah, I don't know why you don't have them. 1 sec. I mean,
You
I
know,
do
it
know
seems that
why.
way.
I know why, because
Before
you started spamming.
I ain't spam nothing.
Can I have admin?
I think we're overcomplicating it using R and P. We should just use MRV sine theta.
We could.
Yeah.
Yeah, maybe if we're just getting confused about the cross product thing, because since it is in 2 dimensions, I see no reason why we couldn't use because wait, am I wrong to assume that you can just use the parallel access theorem to do it?
Like,
Yes, no,
we
maybe
don't.
so.
Do we know the mass? Yeah, we know the mass. We know the radius.
Yeah, so would I be wrong to assume that? Because we can just calculate it about the center of a circle, and then we can just use the parallel access theorem to find it about A.
We find inertia relative to A.
So find inertia relative to the origin first, and then we can find inertia relative to A afterwards. Maybe not. I'm not sure.
But the line of action is not parallel to the center of mass.
So Adam, we're thinking, we're hypothesizing that maybe we can use the parallel access theorem and find the moment of inertia about the origin, and then just use it to calculate the moment of inertia about A. And just instead of using cross product, we can use, since it is in 2D, we can just simply use the normal 2D equations.
So
those would work equally well. Maybe it's just a little bit we're missing something that we would maybe take into.
So you're saying like the angular momentum is equal to the inertia times the angular speed, right? This inertia, angular speed we can just convert. I understand. We can just convert that too. Yeah. But the inertia of this point around A.
Yes. Like we can use the parallel access theorem.
But that would just be this point around A. I don't think it would even be parallel. It would just be the inertia of this point around A. So it would be.
But we only have information around the origin, right?
We can find the distance to A though.
Yes. So would that work?
I think so. I think we can just do this, right? So
let's see if that works.
Wait, guys, how about we simplify it even more and use the MV sine theta thing? Because we have V, we have mass, we have radius.
So yeah, L equals mv sine R mv sine theta. The angle, that's gonna get us the exact same answer as here though. And that's also only gonna get us the magnitude of L. Right? Not the vector, but I
From
guess
the
the other one.
previous answer, like the angle is not 35. It's 17.5.
I
The
think
angle
that's what we
between
need to figure out. Yeah.
yeah.
So, co 17 2.2.
I think they took the radial vector as a line, and that's like 180 degrees, right?
From, like
Like the
here.
radial vector. Yeah.
Yeah, and then found this angle in here. Oh, okay.
We have radius, we have
Which
our
will
angle,
be
we have our x and y components of the mass, so we can just put the x component. So we find our x and y components of where that mass is at that point in time, and then we can solve for the angle. Because the y component will be the same for about a, and then we can just put x component plus whatever the radius was, which is 20 centimeters.
To find theta?
Yeah, to find theta. Oh, I'm thinking the theta around thing, from
Like this?
A to the horizontal.
Oh, from A to the horizontal here.
Yeah, that's what I think. That's what 17.5 is.
I think I know how
There's
they
no
got.
way There's no way it's 17.5 to the vertical, like the velocity vector. There's no way it's 17.5.
How about you extend the radius line? You know when it says 35 degrees, extend it fully, and how about that is 180 degrees?
Yeah, this.
Yeah. If you do that, and then
Yeah, that's 180 degrees, and we know that the opposite angle is 35.
We know that. Well, we know that this is 35. We know that that's 35 degrees. How about I draw it another, not on this picture, because this picture already has that picture on it. So if I have a circle, and here is the point, there is the origin. No, it doesn't like straight lines. No, it doesn't make straight lines for me. There's our mass. So here's this, that is point A. Then we have from here to here is this is a 35 degree angle. We have from here to here is some angle. So we know we're going in this direction with velocity v. V equals 5. This is 0.2. So, yeah, when I take the cross product, it needs to be the angle here. It needs to be this angle. Because this is the radial vector. That's the radial vector there. And that's the momentum. So that angle, well, yeah, that won't make a 90. This will make a 90 here, right? If I draw that nicer. This will make a 90 degree angle there. This will also make a 90 degree angle. But we don't really know how that...
Adam, check DM.
So it'll be more than 90, that angle there, actually. Yeah. Yeah, it will be more than 90. So theta should be more than 90. 35.
The two red things are just perpendicular.
Yeah. That's... So it would be 90 plus 35? Yeah. It would be 90 plus...
Yeah,
the angle
that's what I'm thinking.
90 plus 35.
Mm-hmm.
So I'll just show the picture.
125?
Yeah, that seems to make more sense to me. So how did we not get this before? Yeah. So this is our angle. What we're really looking for is... No, hold on. What we're really looking for is this.
Okay, that's why they did divided by 2. So it's like the 35, but like divided by 2.
But why is it divided by 2? Oh, just because it's halfway past the circle? Just because it's another... That might just be it. Yeah, that it's just a circle thing. If we have this angle here and we move the distance twice as much, it'll be half the angle to get to the same point. That's what it is.
Yeah, that's a rule. Yeah. Wow.
Okay, just draw a triangle with a base of 0.4 as a diameter, and then you find the y by using 0.2 sine 35. Then you have the y and x components.
Yeah. We can find the y stuff. Yeah. Why is it erasing now? Why is it not erasing? Figure out why it's not. Oh boy. Why did that happen? Okay. Doesn't erase for me. Why is it not erasing? That button erases. Sorry, I just want to fix this because it'll be annoying to not be able to erase.
Yeah, the angle will be 17.5. Yeah.
It will be? Just restart OneNote quickly. Okay, now it works. Sometimes OneNote just needs to be restarted. Okay, well then that makes sense. That angle should just be half that angle. If you just think about like a circle property. Yeah, okay.
Yeah, 17.5, yeah.
Wait, but then how does that help us here? Then this angle is also 17.5, right?
Yeah.
So then this angle is...
between the radius, the radial, and the velocity is 17.5. So we can just use the formula.
Yeah. So that's just 107.5 or just whatever to do with cos, yeah. And then, okay, so then it's just the same thing, but here I just do 107.5. Can I go back? No. 0.2 plus 0.2 cos 107.5. Times 5 cos 107.5 minus 0.2 sine 107.5 times 5 sine 107.5. A negative number. Did I punch it wrong? I think I might have messed up the first bit here. Let me just see something. This minus this. 0.2 plus 0.2 cos 107.
Can't see the screen. Why?
Is that for everybody or just, or do you got it?
Oh, you are writing calculator. Oh,
Yeah. I'm not actually showing 107.5 times 5 sine 107.5. Yeah, I got a negative number. I got a different negative number this time, so maybe I'm just typing things in wrong, but I don't think I am. Oh, maybe because I just my brackets. Yeah, okay, I got the same number this time, but negative for just plugging it into here. This position wouldn't change. Oh, wait, so no, it's because I'm, it's because I'm screwing something up here. No, only these numbers are 107.5. It's not both of them. So it's going to be, that should be 35. That should still be 35 times that was 107.5. That is...
Are you writing that in?
What?
Are you writing something in right now?
No, on the calculator. Okay, I still got a negative number. So, which isn't the right negative number.
I think our brains are just fried from this. I think we gotta chill, take it slow. I don't know.
I don't know either. Let's see. Okay, we have this circle. Okay, we have this circle. I'm trying to find, I know the radial vector, I'm trying to find the velocity vector of this. The velocity vector of this is going to be, is it the velocity vector? It's just the velocity vector, like, yeah, it's just the velocity vector. So that is going to be... Wait, how did I end up getting... No. That whole length is 107.5. No. And then that's just going to be 17.5. That's just going to be 17.5 there. We only need that length there. Okay. So now every time I see 107.5, just write 17.5. 17.5. We just didn't realize what it is. I got 1.6 this time. Is it 1.6 the answer? 1.8 the answer. So I did it with these numbers were 17.5. So this is 17.5. This is 17.5.
I think if we round up hard enough, it'll be all right.
Yeah. We just really round up to
Just
the answer.
Just really round up your answer.
I mean, we can be right on every question if we just say, whoever's marking this, just round up to the right answer, and I'm right. So we're good.
Yeah.
Can you summarize?
I don't know.
So one person said summarize. Yeah, I didn't. We haven't finished really, so I don't know how to summarize. We don't have the answer that right. So.
Non-summarize. We don't want anybody to get the wrong. So.
Yeah. So what are we?
If you see this question,
just forget about it.
Nah, just choose the positive of C. It's a giveaway.
Yeah.
So, it's always C, but
much stuff.
What did they do here? Whoever wrote this, Parthy, I think sent this to me. I don't know if it's his work, but so that's just that. Mass is 1. Doesn't matter. M, what is that? MK? R. No, that's R. Oh, what's that? That's a sine. That's a sine 17.5. V 17.5. Okay, V 17.5.
Sorry to interrupt. I keep forgetting. When we do MV R sine theta?
Yeah.
After the angular momentum, is that sine theta the angle between the velocity and position vectors?
The velocity and the radial vector from the radius, from whatever from the axis to the point. Always the cross product is between you have to know what is between, right? To tail to tail between two things, right? So yeah, in this case this is R and this is P, right? So it's between so if you have a radial vector like that and this is your momentum vector, then it's this angle. Theta. Between them tail to tail.
Just point your fingers in the direction of the radial vector and then curl towards the momentum.
Well,
whatever, I don't care.
Yeah, I don't know. I don't know the right hand rule that well, so I don't really know, but we'll figure it out, yeah.
I think we should go now. It's 2:00.
Oh yeah, it is 2:00. Well,
yeah, we tried.
No luck on this one.
We're
try our best, you guys. We need to.
It's all right, everyone. We got this.
Yeah. I remember.
Everyone do bad and they'll curve it. Don't worry.
Yeah.
Thank you, Adam.
That is a strategy, yeah.
But try your best.
That is a strategy. Try your best.
Try your best.
And if that doesn't work, then do bad so that they curve it. There you go.
Try your best to ruin the test, yeah.
Yeah.
I love how we ended on a question that we didn't know how to solve.
Yeah.
It's really good.
Really good way to end the semester. Really good way to end first semester of university.
All
The final touch.
All I want to say is, that's it. All right, everyone have a good test. That's it. You know what I'm saying? It's a
That's
wrap.
the last
It's a wrap
question.
from there.
That's the last question.
Don't fail, guys. Just positive C. That's all.
Guys, just think about it. After this, we have 3 weeks of freedom.
Yeah.
Just think of it as think of it as just an obstacle getting you to the real goal.
Right?
3 weeks off just
suicide.
In like 3 hours, you'll be completely free. In 3 hours, once you're done that time.
3 hours, baby. I'm gonna run it.
Vishal, you're a skimp, man.
Wait, it's a 3-hour exam?
Well,
No,
no,
2 hours.
we have an hour until the exam, and then another 2 hours. So
guys, I'm gonna try to cram a lot more shit now, or else you guys just gonna freaking fry yourselves, honestly.
I'm just gonna take a nap. I'm gonna take a nap for an hour. Yeah, that's my.
Like,
Shovel the
don't
snow,
try to
dude. So
swat
much
some
snow
more
outside.
stuff. It's really gonna mess with you, honestly.
Now my bed is waiting for me.
How possible don't fall during the test.
My advice is to do something relaxing before the exam and let your brain try and like absorb the knowledge
Smoke
that you
weed
just
every day.
gained and all that stuff.
Yeah.
So
Yeah, I recommend go
like,
outside for a walk. It's really refreshing. Yeah.
I'm looking scared, bro.
Yeah, it's shining so bright today, guys. It's like it's a sign.
It's hella cold though. I don't know about you guys. It's hella cold in Canada, bro. You know?
Yeah, it's
Like,
cold.
guys,
Hella
yeah.
snow too.
You gotta get used to it.
You gotta get used to it, man.
Canadian winter.
Bro, I've been here for like 18 years, and I'm still not used to it. You know what I'm saying? Like, yo,
I
it's not in
feel
my
that.